can be implemented in dominant strategies when there are at least three alternatives is the dictatorial one. Okay, so here is what we do. We we allow for multiple alternatives to be implemented in a single state. So this is a departure from dominant strategy implementation, where typically the implemented outcome in every state will be unique. So we allow for social choice correspondences. In other words, for multiple alternatives to be, implemented in a single state. So for all of them to be desirable from the point of view of the planner. So this is, of course, a more permissive notion of implementation. And what we are looking at indeed is implementation in undominated strategies, right? So a notion which has, which has been studied, for instance, by Tillman Borgers in 1991 and Matt Jackson in 1992. So the idea is that every agent eliminates weakly dominated strategies. It's just one round of elimination because it's a private information environment where no agent knows the preferences of other agents, so does not know what the other agents eliminate. So there's a single round of elimination. And note that it's a robust notion of implementation. In particular, it doesn't make any assumptions, regarding beliefs and so on. It's prior free. And multiple undominated strategies will typically exist in every state. And what we are interested in is studying implementation of this kind. And of course, the major complication of this approach is that unlike dominant strategy implementation, we cannot restrict attention purely to revelation mechanisms. Okay, so this is this hugely complicates the analysis. In this paper, we shall focus on finite mechanisms, and more about that very shortly. So here is our contribution, if you will. We provide a general sufficient condition for a social choice correspondence to be implemented in undominated strategies. Yeah. So some necessary conditions are known. For instance, Jackson in 1992 proposed a condition called strategy resistance, which is necessary. Then those have been refined to conditions such as chain dominance by Yamashita, strong chain dominance by Mukherjee, Muto, Ramakers in 2017, etc. So it's known that none of these conditions are sufficient. And so we provide a general sufficient condition, a condition that can be applied in a wide range of environments. And on the other hand, in the literature, it is known that some specific social choice correspondences can be implementable. For instance, the Pareto correspondence, as in a paper by Mukherjee, Muto, Ramakers, and myself in 2019 JET. So the Pareto correspondence and some generalizations are known to be implementable in undominated strategies, with mechanisms which are bounded but not finite. Okay. So what is our contribution? We apply our, well, this is just continuation from what I just said. So we have a sufficiency result. And what we do is that we apply a result to several familiar environments, and we obtain very permissive results. In particular, it is possible to implement a set of outcomes better than those implemented in dominant strategies. So this is one of the things that we wish to emphasize, that focusing on implementation via undominated strategies, can improve or can help the designer attain her goals better than by just focusing attention on dominant strategies. So what do we mean by a better mechanism? So this relies on a normative criterion about ranking social choice correspondences. In particular, we follow a criterion introduced by Borgers and Smith in 2012, and it's a partial ordering of social choice correspondences. We say that a social choice correspondence F outperforms another social choice correspondence G if at every state the designer weakly prefers any outcome given by F to that by G. And at some state, the designer strictly prefers some outcome given by F to that by G. So, very simple and intuitive notion here. At every state, every outcome in F is at least as good as every outcome in G from the perspective of the designer. And indeed, at some state, the designer strictly prefers some outcome in F to that in G. So here is a diagrammatic or sort of schematic representation of what we mean. So on the x-axis are the outcomes F theta and J theta at some state theta, and on the y-axis are, as we go higher up the axis, we have outcomes which are preferred by the designer. So notice that F of theta gives multiple outcomes, whereas G theta, we assume for simplicity here, gives a single outcome. Notice that the worst outcome given by F is at least as good as the outcome given by G. And there are several other outcomes, and the other outcomes in F are actually better, strictly better than those given by G. And equivalently, F is generated by adding better outcomes to G. Okay. So, what are our applications? We show that there are implementable social choice correspondences that outperform the classical or the classic strategy proof social choice functions. For instance, in auctions, single good auctions, we show that the full surplus extraction outcome can be added to the second price auction, and the correspondence can be implemented. In the public good provision problem, we can add the budget balance but efficient outcome to the VCG or pivotal outcome, right? While maintaining, as I said, efficiency and individual rationality. Okay, so and finally, in two-sided matching, for instance, the matching problem, we consider the case where only men's incentives, we consider only the case where men's incentives are considered. But by that, I'll clarify what I mean by this. It means that the preferences of men are private information, while those of women are common knowledge. And what we show that that all stable matchings can be implemented in undominated strategies by a finite mechanism, and we'll briefly discuss why this is actually why this outperforms the man-optimal stable matching. Okay, so here is the related literature. There is a I guess it could be correct to say a sort of small literature on implementation in undominated strategies. Some recent work, particularly important in this, is by Lee and Bojack in 2020. Then I've we put up work in auctions, public good provision, and two-sided matching, which are all extremely well known in the literature. Okay, so let me literature on implementation and undominated strategies. We have a set of agents n greater than or equal to 2, finite set of alternatives. We assume that each agent has a rational preference over A, which is his private information. Script DI is the domain of preferences for agent I, and script D is the Cartesian product of the DIs. Notice that there are no assumptions on the domain. So this is the domain can be completely arbitrary. Social choice correspondence is a mapping whose input is a preference profile, an element of the set script T, and its output is a non-empty set of alternatives. What is a mechanism? We have perforce to consider indirect mechanisms. So a mechanism consists of a message space for every agent. So MI is the message space for agent I, and M, capital M, is the Cartesian product of the message spaces of agents. And the outcome function, which is a map from M to A. So it considers as an input a message profile, and it outputs a particular alternative. And we say that M weakly dominates MI prime at preference Ri in script Di, if it is the case that GMI of GMI M minus I is at least as good as G of MI prime M minus I for Ri, irrespective of the M minus I. Okay, so I'm at least as well off playing MI than by playing MI prime according to Ri, no matter what messages other agents send. And in particular, there is at least one M minus I where I do strictly better by reporting MI rather than MI prime. Okay. So what is implementation in undominated strategies? We say that MI is undominated at Ri if no message dominates MI at Ri. So formally, the definition for implementation is as follows. A message MG implements a social choice correspondence F in undominated strategy if for each preference profile R in script T, A is an F of R if and only if there exists a message profile whose outcome in the mechanism is A, and MI is undominated at Ri for every agent. Okay, so again, I draw your attention to the fact that this is a robust notion of implementation, independent of the prior or its knowledge. And in the specific case that F is a function, we are, we have the dominant strategy implementation problem. Okay. Okay. So, the starting point of this analysis is this very striking result in Jackson 1992, which says that virtually anything can be implemented in undominated strategies. So private information has really no impact on what is achievable. Really striking and unusual result. So so here is a formal statement of the result. A domain of preferences script Di satisfies strict value distinction if for every Ri and Ri prime, if every pair of preferences for agent I which are distinct, there exists some pair of alternatives where there is a preference reversal. So API-B and BPI prime A. And Jackson's result is the following. If Di satisfies strict value distinction for every I, then any social choice correspondence is implementable in undominated strategies. Okay, so everything is possible. But here is the caveat that the implementing mechanism relies on an infinite chain of dominance relations. So in other words, the way that I prevent a particular message from being, undominated at any, at any state Ri, let us say, is that there exists another message Mi prime which dominates it. Mi prime in turn is dominated by some Mi double prime and so on and so forth. So we have, an infinite sequence of messages, and each one dominates the one which precedes it, and it carries on forever. So this is the way that, this construction or this feature of mechanism is key to the Jackson construction. And Jackson himself noted that this was unsatisfactory, and it was natural to impose a restriction on the set of mechanisms. And so the restriction that he imposed was one of boundedness, and the definition as follows: a mechanism is bounded if if for some agent mi and message mi and preference ordering ri, if it is the case that mi is dominated, then it is indeed dominated by a message which is itself undominated at ri. Okay, so you basically cannot have this infinite chain of messages which dominate the preceding message. And a trivial observation: a finite mechanism is always bounded, because by definition we cannot have an infinite chain of messages, each one dominating the preceding message. And throughout the paper, we shall focus on finite mechanisms, so that our focus is on bounded mechanisms. Okay. So as I had mentioned earlier, the main result in our paper is sufficient condition for implementation by finite mechanisms. And the sufficient condition is based on three properties. One is strategy resistance, which I've already introduced and indeed was introduced by Jackson. Then strategy proofness of range top selections. And finally, a flip condition, which you might think of as a slightly stronger version of the strict value distinction condition in Jackson. Okay. So let's begin by defining strategy resistance, defined in Jackson 1992, which you should think of as a monotonicity condition on correspondences. So what does it say? Let's pick some agent I, and let's pick some R minus I, and let's keep it fixed. And imagine that I changes her preference from Ri to Ri prime. Now pick an arbitrary A in f of Ri R minus I. Then when the agent changes her preference to Ri prime, there must be an alternative in the value of the social choice correspondence at f of Ri prime minus Ri, such that B is at least as good as A according to Ri prime. So in other words, there must be something in B which is at least as good as, there is some B in f of Ri prime R minus I, which is at least as good as anything in Ri R minus I according to Ri prime. Okay. So, so this is, here is a 1 minute proof of it. So suppose A is implemented by an undominated message Mi at Ri, and let I's preference change from Ri to Ri prime. Then if Mi is undominated at Ri prime, then in fact, the outcome by the definition of implementation, it must be the case that A belongs to f of Ri prime R minus I, and of course A is at least as good as A according to Ri prime. So that case is easy. Now suppose Mi is not undominated, in other words, it is undominated, then by the definition of implementation, there exists some message, let's say Mi prime, which is itself undominated, such that Mi prime dominates Mi at Ri prime. Okay. So let's so let the outcome when this agent plays mi prime and the others are playing whatever they were playing earlier, m minus I, let the outcome be b. So by definition, because mi prime dominates mi, it must be the case that b is at least as good as a according to ri prime. So this shows that strategy resistance is indeed necessary. Okay. Here is another very critical element of our characterization. Let's fix a social choice correspondence F and let Ti be the social choice correspondence such that for each preference profile R, TIR is the most preferred alternative in F of R with respect to Ri prime. Okay. So we say that Ti is a range top selection for I from F. So what is very simple. We look at every R and we pick an element which is Ri maximal in F of R. Or equivalently, F is generated by adding to Ti worse alternatives with respect to agent I's preference. So at F of R, Ti R is is an alternative which is Ri maximal, and then F contains some other elements which are worse than Ti than TIR according to Ri. Okay. So here is a very important observation regarding the range top selection, that which is the following. Suppose F satisfies strategy resistance. Now, then agent I cannot gain by misrepresentation of her preference in Ti. Okay? So this is very important. Why? Because why is it? Because we know that there exists some element in F of Ri R minus I, which is better than F of Ri prime R minus I according to Ri. This is strategy resistance. So when we are taking the best outcome according to Ri, that must certainly beat everything that that the agent can obtain by deviating to Ri prime. Every element in F. So in particular, it's also better than the best element in F of Ri prime R minus I according to Ri prime. So agent I cannot, Ti is a social choice function, and I cannot do better by misrepresenting her preference in Ti. However, Ti is not strategy proof. In particular, agent J not equal to I could perhaps manipulate Ti by changing her preference ordering from, let's say, Rj to Rj prime, because this changes the range of F. Then Ti would again select a maximal element according to I's preferences, but agent J could benefit by restricting the range over which this best element is chosen. Okay, so here is the key to our approach. Here is what we do is we exhume the existence of a strategy proof Ti for each I. So here is where we depart from the necessary condition. We tighten it, or we make a further, we strengthen it beyond what we know to be necessary. And then what we do is that we add alternatives that are worse than Ti for each I. Okay. And however, these added alternatives, although they are worse for I, they may be better from the point of view or from the perspective of the planner. So we fatten the social choice functions Ti by throwing in some more elements which are worse than Ti for each agent I. And what we do is that we implement the fattened correspondence. Okay, so here are some examples. In the social choice environment, TI is, let's take the case where TI is dictatorial. So this is obviously strategy proof. And what we can do is that we can add other alternatives which are worse than I, but which could be Pareto efficient. We could add an alternative which is perhaps second ranked by all agents if the first ranked alternatives are all distinct. We could add the full surplus extraction outcome to the second price auction at every valuation profile. And in the public good provision model, we can add an efficient budget balance outcome to the VCG outcome and add all other stable matchings to the man optimal stable matching. Now, the critical feature of these examples is that the range top selection in each case is strategy proof. For instance, in the auction case, the second price auction outcome, that SCF we know is strategy proof. Now, if we add the full surplus extraction, then the agent who actually has to pay her full valuation is going to be worse off. So it's going to be a worse outcome. It's going to be better from the perspective of a planner who wishes to raise revenue, but that fits in exactly with what we were saying. Similar observation for the public good and the stable matching, because we know that the man optimal stable matching is the best matching as far as for men, and the worst for women. And we also know that the man optimal stable matching is strategy proof. So any other stable matches that we throw in are actually more favorable, are worse for men, but could be preferred by the mechanism designer. Okay, so here is our definition. The critical definition: extended strategy resistance. We say that the social choice function F satisfies extended strategy resistance if F satisfies strategy resistance, and for each I there exists a range top selection TI such that TI is strategy proof. Now, one question that might strike you is why do we need to assume both of them? My previous comments may suggest that two actually implies one, but actually it doesn't. So condition 2 does not imply 1 in the definition, so we need both conditions. And so we have this additional condition called the flip condition, the counterpart of the value distinction, the strict value distinction condition, if you will. So social choice correspondence satisfies the flip condition if for each agent I and each Ri prime in script Ti satisfying Ri not equal to Ri, in other words, Ri and Ri prime are distinct, there exists a pair of alternatives X and Y such that there is a weak reversal between X and Y in Pi in Ri versus Ri prime. In other words, X is strictly better than Y in Pi, and Y is weakly better than X according to Ri prime. And furthermore, for each agent J not equal to I, there exists a range top selection Tj of J from F such that for all preferences profiles R bar, we have that Tj of R bar is at least as good as both X and Y. Okay, so in other words, X and Y should not be better than the range top selection of agents J not equal to I, right? So the preference reversals should take, we demand preference reversals for agent I. However, these preference reversals should not be, should not upset the range top selections of the other agents. So in other words, J not equal to I dislike X and Y. So note that X and Y need not be in the range of F at any profile. So we can see that it can be satisfied in many economic environments which involve payments, because J not equal to I, all agents J not equal to I may have to pay something or whatever. Okay, here's our theorem. A social choice correspondence satisfying extended strategy resistance and the flip condition is implementable in undominated strategies by a finite mechanism. Okay, so that's all you need for implementation by in non-dominant strategies by a finite mechanism. So let's consider our applications in more detail. Auctions, provision of public goods, and two-sided matching. Um, so let's consider auctions. N bidders, private values, quasi-linear utility. Theta I is bidder I's valuation. We discretize types. So theta I is belongs to the set theta 1 to theta k. We do this because we consider only finite mechanisms. We do have a section in the paper where we consider the standard type spaces, continuum, and so on. But obviously, then we cannot insist on finite mechanisms. So we show that our results in that setting can be extended to bounded mechanisms, bounded but not finite. And the second price auction SCF, right? So this is the outcome, F 2R theta with reserve price. So this is a social choice function which at the valuation profile theta gives the object to the highest bidder, to the highest bidder at the price of the second highest bidder, where you can imagine that the seller also puts in a bid of R. Okay, and so if we know from the fundamental result of Myerson 1981 that if the environment is symmetric, then this auction, the second price auction with the reserve price, is one which maximizes the expected revenue of the seller. Okay, now here is what we do. F1 theta will be the social choice function, which is the first price auction outcome when we assume truthful bidding. So what we do at every valuation profile, we look at the highest bidder. This person is given the good and is charged her valuation. Okay, and F of R theta is the union of these two outcomes. So F2R theta, which is the second price outcome with reserve R, and F1 theta, where the highest valuation bidder gets the object and pays her valuation. And it's easy to verify. It's almost obvious that FR outperforms the second price auction F2R, right? So, the worst that can happen in capital F of R is F2R, and in terms of revenue, and F1 theta gives strictly more revenue to the planner, and by applying our result, we can show our sufficiency result that the social choice correspondence F of R is implementable in undominated strategy by a finite mechanism. And again, the key to this result is the fact that F2R is a strategy proof. We know that the second price auction SCF is a strategy proof. And we know that F1 theta, they include outcomes which are worse or certainly no better than the outcomes given by the second price outcome. Okay, because those who are not given the good pay no differently from what they were earlier, and the person who gets the object now strictly pays something greater than what he would in the second price auction. Okay, in the public good problem, again, totally standard private values, quasi-linear utility. We consider binary decision for the public good. P equal to 1 means the good is provided. P equals to 0 means the good is not provided. And theta is the valuation of the public good. Again, we discretize types with the same observation that we made for auctions. We can extend it to continuum of types by weakening finiteness to boundedness. And P star theta is the efficient decision. Oh, I must add that in order to provide the public good, you have to pay cost of a cost C. So P star theta is equal to 1 if the sum of the valuations of the agents exceed C, and 0 if they are less than C. And the pivotal or VCG payment will be denoted by T of VCG. So the VCG SCF is the efficient decision together with the VCG payment. We all know that it's efficient, it's strategy proof, it's ex post individually rational. However, it's not budget balance. It runs a deficit. You have to import money from outside. And this is, well-known deficiency of the VCG. So what we do is we consider the first best SCF P star. So the public decision is efficient, but we consider a particular payment scheme such that the sum of payments is equal to P star theta C. In other words, people pay nothing if the payments exactly cover the costs when the public good is produced, and don't pay anything if don't pay anything if the good is not produced. And let's consider the f of theta, which is the union of these two alternatives, the P star theta T of VCG theta and P star theta of T of f of B theta, right? It's the union of the VCG and an efficient budget balanced and individually rational outcome. And again, an application of our result yields the following. There exists a first best social choice function P star TFB, right, such that the social choice correspondence F is implementable in undominated strategies by a finite mechanism. Okay. Good. So finally, an example with a slightly different flavor. So we consider the two-sided matching problem of Gale and Shapley. Men 1 to N, women W1, W2 to WM. Each agent has a strict preference over the set of agents on the other side, along with the outcome of remaining single. And we focus on the men's incentive problems, and in particular that women's preferences are known and fixed. The man optimal stable matching SCF is strategy proof for men. And it's also well known that other stable matchings exist. So let script S be the social choice correspondence, assigning all stable matchings at each preference profile. Again, since in all other stable matchings, women will be better off relative to the man optimal stable matching, it is the case that if the designer respects women's preferences, then S outperforms the man optimal stable matching SCF. And again, an application of our result yields the following. The stable matching SCCS is implementable in undominated strategies by a finite mechanism. Indeed, any sub-correspondence F of S is also implementable if F contains the man optimal stable matching SCF. Now here, a small remark about the X and the Ys that we have to choose, which ensure that they're not better than the range top elements of agents J not equal to I. So what we'll do is that we will give the outcome where all agents J not equal to I are unmatched, and we will take advantage of the fact that that stable matchings are always individually rational, right? So that will not upset PI for any J. Okay, so that's what we will use. Okay, so finally, let me make a few very brief comments about our mechanism, which is really the heart of our paper. So the mechanism is a sort of refined version of the modulo mechanism used by Borgers in his 91 paper, which he used to implement the top rank social choice correspondence, which assigns the most preferred alternatives of all agents at every profile. So what's the modulo mechanism? Each agent I simultaneously announces an integer Qi along with his preference, and the integer profile selects a dictatorial mechanism. In other words, given the integer announcements, we are able to construct. We use that to identify a dictator by typically looking at the residue of the sum of the integer announcements mod n. And then this agent is the dictator in the selected mechanism, right? And so here, it's quite easy to see that that announcing something which is not truthful is always dominated by truth telling, and then truth telling and an integer announcement is it cannot be dominated. Okay. So in our case, our implementing mechanism has a similar but significantly more complex structure. So each agent simultaneously announces an integer, a color, and two preferences. And the integer profile selects one of several sub-mechanisms, right? And these sub-mechanisms have the same message space, right? So you announce a common message. So you announce messages and an integer. This integer then selects the sub mechanisms, and your message, and your the other elements of your message profiles then leads to the outcome in the particular sub mechanism that the integer announcements lead you to. And we have to use a refinement of the modulo game, which we call the extended modulo game. And in the selected submechanism, the final outcome is specified according to the announced preference color profile. So, so let me summarize. So what we investigate is implementation in undominated strategies by a finite mechanism. We provide a tractable sufficient condition for implementation, and we develop a method for constructing and implementing mechanism. And we find implementable social choice correspondences that outperform the classic strategy proof ones. And in auctions, we outperform the second price auction. In public good provision, we outperform the VCG mechanism. And in two-sided matching, we outperform the man-optimal stable matching. Okay, that's all I have to say. Thank you.
Okay. Do you hear me?
Yeah.
Okay. So thank you very much, Arunava. Unmute your microphones and have an applause for Arunava. Okay. So I'm looking at the chat. There are no items in the chat. So does anybody have a question to Arunava? Yeah, Francois, can you unmute your microphone and ask your question?
Yes. So first, thank you, Arunava. Excellent, very interesting talk. So I have sort of two quick questions. So I understand that at each profile, the set of undominated strategies, I mean, there are several undominated strategies. And my first question is about, is it possible to compare them, or are they undistinguishable from the point of view of the set of alternatives that result from that? So, I mean, maybe more precisely, is it the case that the set of outcomes that are possible, let's say that I have two undominated strategies, if the set of outcomes associated to the these two strategies is the same, I think that it's fine. There is no way for me to distinguish between the two, but assuming they are not the same, maybe, an additional criterion that undominated may make me prefer one over the other in a kind of probabilistic sense, for example. And so I would like to see whether the set of strategies that follow the choice of which undominated strategy I'm going to play differ. And my second question is, from the point of view of the designer, let us assume that I prefer the alternative that is not in the top of the individual. So that are not those strategy-proof ones. For example, because I like the compromise. Is there a way for me to design the mechanism in the sense that I increase the likelihood that this is the outcome?
Good question, Francois. I mean, I'm afraid the answer to both questions is no. I mean, in the sense that all we can ensure is that the extra messages that you throw in over the range top selection ones are undominated, right? I mean, they may be undominated because there is the way we construct it by showing that there exists some possible messages of the other. It may just be one where by playing the compromise outcome, you do by the compromise message, you do better, right? So the basic thing is that you have these range top selections and you want to play those, but you want to make certain other messages undominated. How do you do that? You make sure that there is some eventuality, some m-i, whether we're playing, let's say, the compromise message does strictly better than that one, right? But it may be just one. I mean, for us, it's enough to show there is some m-i where you do better, right? So in fact, if you just count the number, it may be that the strategy proof one is actually doing much better. So I'm afraid these are all questions which have to be addressed perhaps in the future and so on, right? But the point of our paper is that you can do it. I'm sure there are all kinds of other refinements which one needs to which one needs to consider seriously. But so far, you can say that all we have is an existence result, where what we do is that we manage to ensure that these compromise messages do not end up getting knocked out, do not end up getting dominated. That's all. And so I think that's really, as far as the message of our paper is concerned. Although I think that all these refinements that you suggest, how do you make this more attractive in some sense, according to some criterion, these are certainly questions which, one can think of, as and trying to address them. I don't know if I've been, answered your question satisfactorily, but yeah.
Thank you. Yes, thank you.
Yeah. Okay. Thanks.
Okay, are there any other questions by the audience?
I have a quick question. Thank you, Arunava, for the talk. Extremely precise and so forth, and we understood. I mean, most of it was good. We understood everything. Now, when you describe briefly at the end your actual mechanism that does the job,
yeah.
Well, you didn't go into detail because it's complicated, but the guess is that when you apply this mechanism to something like improving the VCG to get full surplus or the public good example, maybe there the mechanism is not that complicated. Or am I completely wrong? And the mechanism is equally difficult to explain or equally long in that case. Does it have the number of possible types? If I have, let's say, only 3 types each, then it's not too complicated. Then it grows exponentially. Is there some kind of complexity idea of the mechanism you use?
Well, I mean, yeah, I mean, the message spaces can all be bounded, they're polynomial in the parameters of the problem. So it's not it's not exponential in that sense. But I mean, we've honestly didn't explore the idea of, push this idea of simplicity, can we do something more simple? We have a very specific example for the case of the stable matchings, right? So the idea is that you construct a baseline mechanism which consists of the range top ones. Now, what you want to do is that you want to add certain outcomes which are better from the designer's perspective, which are, let's say, women optimal, but are not men optimal. So they will tend to get dominated. So then you have to add certain other mechanisms where those are, those don't get dominated. And then the integer announcements make sure that these compromise messages, let's say the women optimal messages, don't get knocked out. That there will always be some eventuality, which is this thing, where those messages will survive, will not get dominated. The problem is, as soon as you add these other, messages, there is a tendency for them to get dominated, because they are the range top selections sitting there, so they may get knocked out. So somehow you have to smuggle the other things in to make sure that they are knocked out. So it is a bit of a brute force. It is not a terribly sophisticated idea in that sense. But you can do this all with some version of not just a modulo mechanism, but a refined version of that, which we call the extended modulo mechanism. So the idea is that every time you take any two integer announcements of a player, there exists an integer announcements of the others, such that you end up playing the same mechanism for Qi and Qi prime. And it's, I mean, there is some stuff that I like there, which involves using mod 6, you have to use these integers mod 6, and that turns out to be very useful. So, I mean, I hesitate to say that this is something which is, practical in the sense that we can tell people, look, play this, look, this is undominated, etc., etc. But, at a theoretical level, the idea is quite straightforward. That's all I want to say.
Oh, sure. Yeah. Thank you. No, that's clear.
But I mean, in the paper, which I'll be happy to send you, I mean, there is an example of the matching case, where we actually show exactly how to do it, and it has only a few types. I think it's more easily understandable.
Okay.
Yeah.
Thanks.
Okay, are there any other questions?
Yeah, I had one quick question about the matching. So you mentioned for matching problem when the preferences of the women are common knowledge, that you've got this implementation, and I was curious, for the marriage problem where all preferences are unknown, is the correspondence of the stable matchings implementable?
No, well, you have to build on a strategy-proof social choice function, right? So
I thought it was you could do maybe man optimal for the women and or man optimal for the men.
But you need one thing which will work for both. So I mean, so it's not going to our approach won't take off. I mean, at all there. But if you restrict yourself to one side of the market, then we know it's strategy proof. So the basic idea is to build on something which is strategy proof. And if there is a basic message, is that once you have something which is strategy proof, you can build on that and throw in a lot of other stuff which agents don't really like, but the planner may like, and you can implement the whole thing. And the ideas are in some sense related to the old stuff on complete information implementation. You need some preference reversality somewhere, and you can exploit that, and everything works to get around the sort of the requirements of boundedness, finiteness. You can do that. I mean, that's Yeah. But you need something strategy proof to start with, and it would be very interesting to see what you can do. I mean, we do. I mean, what you're suggesting could well be, you know, it's entirely possible that you can do it, but we don't have an answer. We don't have an answer.
Okay, more questions. I have a question, Arunava.
Hi,
in your presentation, you talk about the preferences of the planner and also sometimes your answers. But
yeah.
I don't see those preferences of the planner coming back in the formal model. So is this just something that you use in applications, or is it just by way of manner of speech or something like that?
Yes, I mean, it's not in the model. I mean, you know, the formal result is simply about social choice correspondences which are implementable. That's all. So there is no, you know, the preferences of the planner play no role in that result at all. But in the application, you're absolutely right that the application is you know, where we give the planner some preferences. So for instance, you know, he or she likes more revenue, or you know, has some regard for the preferences of women or something like that. So that's you know, really, you might say motivation, but the result is about implementing correspondences.
Yes. Okay. Okay. Thanks. More questions? If not, then I guess we want to thank the speaker once again. So unmute your microphone.
Thank you.
And then I suppose I close the session. So I'm looking or expecting the host to.
Okay. Thanks.
I guess we're going to the breakout rooms or something like that.
I think we're running a little bit late, so we can probably just go directly to the next talk, and then we'll have a break after the talk so that we can start gaining on time. Okay?
Thank you.
Okay, thank you.
Thank you, Hans, and thank you, Arunava.
Thank you.
So our next talk is going to be the Arrow lecture for this year. The Arrow lecture is going to be given by Jordi Massó, who is a professor at the Universitat Autònoma de Barcelona. I think everybody knows here Jordi. He's been at Barcelona since 1989 after receiving his PhD from Stony Brook. He's associate editor of Social Choice and Welfare, the Journal of Dynamics and Games, and Mathematical Social Sciences. His work on mechanism design usually analyzes incentives and also normative properties of mechanisms, specializing in social choice theory, matching, and allocation of divisible goods. The work that he will be presenting today belongs to this last category, titled All Sequential Allotment Rules Are Obviously Strategic Rules. So I'll start the presentation by Jordi, and afterwards we'll have a couple of questions and a brief session with Jordi.
Good morning, I'm Jordi Massó. For me, it's an honor to be here today presenting my work. I had always felt extremely attached to the society. I still remember the meeting in 1992 in Caen, where Ken Arrow was giving his presidential lecture. So I felt very honored when I was asked to present the paper in the Mexico meeting. So I'm going to present today this paper, which is a joint work with Pablo Arribillaga and Alejandro Neme. They are both at the Universidad Nacional de San Luis. San Luis is in the middle of Argentina, it's a city and a state. So the main goal of the paper is to show that in the division problem with single peak preferences, all sequential alignment rules are obviously strategy proof. In order to give content to this statement, I will first describe briefly what is a division problem with single peak preferences. Then I will describe, give you a bit of taste of how those sequential alignment rules work, and describe what's the meaning of obviously strategy proofness, and then state the result and give the main idea for a particular case. So the problem, the division problem is extremely simple. We have a fixed number of indivisible units of a good, and we have these two. So this is an integer, and these units have to be allotted among a set of agents. And the problem is that we are looking for an allotment that is a feasible allocation that distributes the k units among the set of agents. So observe that we are assuming that there is no free disposability. So the full k units have to, the entire set of k units have to be distributed among the set of agents. This is a particular instance of what has been known as the private good case. So social alternatives now have individual components. And if there are no external effects, makes sense when an agent I is comparing between two allotments, which are the social alternatives, and in these two allotments he receives the same assignment. Now the agent is indifferent among those. Observe that this gives already extremely large number and large indifference equivalence classes, and this is the reason that in this setting we will be able to identify mechanisms that are not only strategy proof, but even obviously strategy proof. We are far away of the universal domain hypothesis, so Gilbert-Sutton weight does not apply. But not only for this private good case, but also I'm going to assume, in addition, that preferences are single peak, so I can assume, yes, that the preference of the agents are defined on the set of potential assignments, units of the wood, and the assumption is that the preferences are single peak. That is, there exists the top assignment, the best one, and moving away in either of the two directions, the agent finds worse assignments. So this is the hypothesis of single peakness. So calligraphic R will be the set of all single peak preferences. So there are many situations. Usually this has been identified as a restricted model of a more general setting. Yes? Situations where agents might share a good, a bad, or a task, like the surplus of a joint venture, the cost of a public good, the division of the job, or just rationed goods traded at fixed prices. A prototypical example is when the agents are workers who already have collectively agreed on a particular number of hours that they have to put on the system, and quasi-concave preferences on the space of hours of leisure and money coming from the hours that the agent will work induce single peak preferences on the set of hours that the worker will have to work. There are many other examples in the literature. This has been extensively studied in this model. Yes. So now, given fix a problem with KIN, now let's look at now the profile of tops. Yes. This is a profile of tops. In general, this profile of tops will not be an allotment. It will sum up more or less than K. Yes, so we'll have a situation of a scarcity when the sum is larger than K, and a situation of excess when the sum is smaller than K. Yes, and the question will be how to determine everybody's assignment, taking into account only the single peak preferences on the agent. That's the question. Yes, this is the discrete version of the model presented by Sprumon in Econometrica 91. In a Sprumon model, the wood that has to be shared is completely divisible. So we have a number K that can be splitted in any ways, not necessarily in integer units. So the way to solve the problem is by specifying a systematic way of selecting an allotment for every preference profile, and this is exactly a rule. The first requirement is that we like that the rule induces the true revelation of the preferences. Yes, that is a strategy proof. What does it mean? It means that indeed truth-telling is a good predominant strategy in the direct revelation mechanism. It never pays to declare for an agent another preference. It will be always getting the same or even worse alternatives. So the second natural requirement is to ask for efficiency. And the rule is efficient if it is at every profile, select the Pareto efficient allotment. It's easy to see that when coupled with single P preferences, efficiency is equivalent to same-sidedness. That is that when there is a scarcity, that is when the sum of the tops is larger than K, then everybody should have to receive less. And when there is excess, that is the sum is strictly smaller than K, then everybody should receive more. So the rationing is always, everybody is in the same side of the ration. Either everybody receives more or everybody receives less in the case of scarcity, right? So the next property, so as Prumon showed that in the continuous version, if we add to strategic goodness and efficiency the property for anonymity, there exists a unique rule satisfying these three properties. This is a uniform allocation rule. There are many settings in which, however, that perhaps anonymity would not be a natural assumption to make. For instance, agents may go with some part of the wood into the system. So there are originally rights on some amount of the woods, and the total amount of the wood that has to be distributed is precisely the sum of these individual amounts. And so in these cases, anonymity will not make sense, and also would not make sense if we want to respect some type of seniority, we want to, for equal opportunity reasons, and so on and so forth. So the problem is that if we don't have anonymity, then the set of a strategy proof and efficient rules is extremely large. We don't even know how is this class. I think it's not known. However, if we add some type of fairness requirement, then we have a complete understanding of this subset of a strategy proof and efficient rules. And this fairness requirement is replaceable monotonicity. Yeah, it says a rule is replaceable monotonicity if for all profiles of agents and any potential alternative preference submitted by the agent, suppose that the agent increases his assignment. Since these two have to be the image that these two profiles have to be an allotment, if he receives more, it means that somebody has to receive less. The action will say then everybody should receive less. Yes. So if agent by changing the allotment gets more, then everybody should go in the same direction. Yes. And of course, if we apply twice this requirement, it says that if the changing the declared preference, the agent doesn't get a different assignment, then it means that the full allotment has to be the same. And this is what has been known as a non-bossy rule. So for this particular setting, then, when this total amount that has to be distributed, K, comes from precisely the units that everybody puts on the system, the individual rationality assumption makes a lot of sense. That is, the rule has to have the property that every agent receives an assignment that is at least as good as the units that he is putting in the system. Yes, so this is a notion relative to particular allotment. We have an allotment, individual rationality says that everybody should get something that is at least as good as the assignment at this allotment. And Topsoli says that only depends, the rule depends only on the top, and so if this is Topsoli, you can write just the rule of using notation as just depending on the tops. The paper this paper in Gaines by Barbara Jackson and Neme, what they do is just characterize the set of strategy proof, efficient, and replacement monotonic rules as the set of sequential allotment rules. If in addition, they also show that if in addition we ask for individual rationality with respect to particular allotment, then the class reduces to the subclass of sequential allotment rules where the rule at the extreme profiles where nobody asks for nobody asks at all anything. And the profile where everybody asks for everything, the rule has to give exactly this Q. And so among all the set of sequential alignment rules, if we add, in addition, individual rationality with respect to Q, now we will have to restrict the rule satisfying these extreme properties at these two extreme profiles. Yes. So sequential alignment rules might be thought as starting as a sequential process of assigning, allotting the units of the wood in a sequential process. And this sequential process will start from two reference allotments. Yes, the Q upper bar is the reference allotments, guaranteed allotments for the agents that are used whenever there is a scarcity. And the Q lower bar is going to be the excess guaranteed allotment that is going to be used whenever there is excess. Yes? So if these two, so we have a profile, we have to use one or the other. If this one is not efficient relative to this profile, is not efficient, then it means that the rule has to correct to make efficient Pareto improvements. And the rules differ precisely on this pair of starting reference allotments and how this efficiency correction takes place. And this is why there are going to be many, many, many rules. In particular, you see for every pair of allotments, we'll have different rules. And not only that, even rules sharing these two reference allotments, there will be different rules that solve the efficiency adjustment in a different way. Yeah. So how is this rule? I'm just going to give you the main intuition of how do they work. We have these two allotments as a reference. So take a profile. If the sum is equal to k, the rule has to select exactly this allotment. If the sum is still larger, so we have a scarcity and the symmetric case for the other case, then what we have to look whether what is the set of agents that is asking more than this guaranteed allotment. If this is everybody, then the rule gives exactly at this profile this guaranteed assignment. If not, then we have to look who is asking for less. Now those guys will receive exactly the top and they will leave. Now the remaining units that have not been allotted by giving the top to those guys, now we will have to be distributed among the remaining agents. Perhaps, and we keep doing until we finish the process. So perhaps the best way of understanding is just look at an example. 4 agents, k units to be allotted, and now we are going to assume that we will have a scarcity. So let's consider this allotment, that is an allotment, and assume, so we can represent this allotment in this figure. This is the set of units, and this is what receives agent 1, agent 2, agent 3, and agent 4. Yes? So this is a way of representing an allotment. These dots will have to sum up equal to 7 if it is an allotment. But we can also represent the profile of top. This is not going to be an allotment, but this is agent 1 gets 5, 1, 2, and 2. Yes? So how the sequential allotment rule proceeds, we have to identify what is the agents that are asking for less than the reference allotment. In this case, or equal. In this case, it's agent 2 and 4. Yes. So what we do, we give exactly these units to agent 2 and 4, and they just take those and they leave. Yes. Observe that now they are living with 2 and 1. So observe now that we have to allocate now. There are 3. So we have to reallocate these 4 units. But agent 3 already has here a guaranteed allotment of 1. So now we have to increase the guaranteed allotments of the agents that remain, 1 and 3, these additional 3 units that have to be allotted. In this case, so we are giving 2 additional units to Mr. 3 and 1 additional unit to Mr. 1, correct? So in this way, we have allotted the 4 units, and this is going to be a feasible allotment together with already distributed units. And now we have to look what are the set of agents that is asking for less. And in this case, it's agent 3, so we give the top to agent 3, so it is 2, so 2 plus 1, we have allotted already 2 units, so now we have to increase in 1 unit the reference allotment, guaranteed allotment of agent 1. Since he's the last one and he's asking for 4, he's going to receive exactly these 2 units. Observe that in this case, there are several properties. We can just see on the rule by looking at the example. The first one is that either everybody receives the top. Those are the agents that live along the process of this, along this sequential process. And so either the agent receives a top or receives something slightly less. And this is same-sidedness, which deals with the efficiency of the rule. Replacement monotonicity is captured by this idea, this property that the rule is reallocating the leftovers, that what has not been still assigned, in a monotonic way. So the reference allotments, the warranted allotments, are increasing monotonically in this case. Yes. Strategy provenance is obvious. Those guys already have the top. So let's look at somebody who is above, in this case, his top is above of what he receives. Observe that moving around is not producing any effect. The rule is constant with respect to any top on the right-hand side of 2 units. However, he can move only by moving in the other side, but this doesn't want, but agent 1 in this case doesn't want because he has single peak preferences. Yes, so this is the reason why they are strategy proof. By definition, there are stops only, and in particular, we think a little bit, in this case, everybody will be above the reference allotment, so the rule will select the Q upper. Yes, so Lee, in 2017, presented this, what has been in this short period, relatively influential paper, by looking or by proposing an alternative notion that is obviously strategy provenance, that wants to capture the fact that solve a little bit the problem that in the direct evaluation mechanism, to identify for agents that truth-telling is a dominant strategy may be relatively complex because it requires a lot of contingent reasoning. Everything happens, all the process of revelation happens in the heads of the agents. There is no partial information about how the preference of the agents look like, so everybody has to imagine that what happens if the others did something, what is my optimal decision? Yes. In order to solve that, or at least to provide mechanisms where the identification of the truth-telling as a dominant strategy is easy, he proposes this notion. This is an observation that were already done in the literature, for instance, in sealed bid second price auctions. This was the proportion of agents truth-telling is significantly smaller than, for instance, using the sequential ascending price English auction. Both give the same outcome, but to realize that truth-telling is a dominant strategy is easy in the ascending price auction because partially information is revealed. I don't have to have hypotheses what the others are doing. I see what they are doing. They're still in the race, so they are still willing to pay the amount where the price that is going up, it shows up now. So a rule, I'm going to define obviously strategy provenance in this particular setting already. So a rule is obvious strategy proof if this is an extensive form game, so we are looking for sequential mechanism. The set of players is n, the set of outcomes is the set of allotments, that has the following property. For every agent and for every preference that the agent may have, I should be able to identify a particular behavioral strategy in this game, with the property that once I do for everybody, and everybody plays according to this strategy, the outcome of the game is the allotment that would have been selected by the rule precisely at this profile of preferences. And second, this behavioral strategy is obviously dominant in the extensive form game. And this is what is the new concept, what it means to be obviously dominant in extensive game form. In this case, then the game we say that OSP implements the rule. Yes, what that means. Suppose that now we have an extensive game form. And so suppose you will see that this is very simple in our case. This is very, this is a strategy, that a behavioral strategy in this extensive form that can be attached to the behavior according to particular preference of the agent. Yes, so let's look at this strategy. Now consider any other strategy. Yes, so now let's look at, so since these two strategies are different, it means that at some place some node, let's assume we can do it assume that this is a perfect information game, and so there exists a node where the two strategies differ for the first time. So this is an earliest point of departure between these two strategies. Yes. So let's be here. So observe that perhaps these two strategies this agent has played before, but in this case, it means that if this is the earliest point, it means that the two strategies are behaving the same way. Or perhaps there are other earliest point of departure because other player that was playing before made different choices. Yes, but now assume that we are an earliest point of departure between these two strategies. The two strategies prescribe a different behavior. So the hypothesis to define obviously dominance is that, okay, let's look at the consequence from the point of view of the agents of choosing according to this behavioral strategy. What he does now is he's very pessimistic. So what he's going to look at is for all possible outcomes that may emerge as a consequence of the behavior of the others and his behavior using this particular strategy along the path. Yes, so there are many possible outcomes. Xi is the worst. Yes. Now, in contrast, he's very pessimistic. In contrast, he evaluates the alternative strategy in a very optimistic way. That is, he looks for all potential outcomes that may follow this choice, and Yi in this case is going to be the best possible outcome among all those possible ones. Yes. And the requirement is that agent I should feel this worst possible outcome associated to this action, and this as good as the best possible outcome associated to this action. Yes. So whenever he's here, if this is the case, means that all those outcomes are better than all those outcomes. Pair by pair, take one here is at least as good as any one of here. So when it's here, the choice that is prescribed by this strategy is obviously optimal. In this case, this other choice. So obviously dominant require that this strategy is obviously dominant in this extensive game form for any alternative strategy, and for every earliest point of departure, this is the case. Yes, the pessimistic way of imputing the consequence of this strategy is at least as good as all the potential outcomes of behaving differently, in particular the best one. Yes, so this is the notion of course, this is going to be very extreme behavioral hypothesis, and hence is going to be very demanding requirement. Yes, so the literature has already shown complete impossibility results. Yes, for instance, Leeat himself showed that the top 3 cycles, that is a strategy proof, but it is not obviously strategy proof. As Lagin Korunzowski showed that the ferret acceptance algorithm looking for only the incentives of one side in the market is a strategy proof, but it's not obviously strategy proof. There are also partial results, partial possibilities that essentially restricted the domain where those mechanisms are applied, and even in the original paper, Lee has a positive result on a particular setting of binary allocation problems with quasi-linear preferences. There are also, so the difficulty, part of the difficulty of this notion is the fact that we have to show the existence of a game in extensive form. For strategy proofness, the reversion principle tells us that we don't have to worry. We have to just concentrate on the direct revelation mechanism, and that's all. Ask that truth-telling be a dominant strategy. Here, the notion depends on the existence of this extensive form. And hence, this is one of the difficulties. So this explains why there are several papers that have been looking for revelation principle-like results to apply the notion of obviously strategy proof. And one of those papers is precisely Mackenzie. It's a beautiful paper in which he gives the family of rules, of mechanisms that one can restrict with a loss of generality if he's looking for obviously strategy proof mechanism. And there are other results also. So the main theorem of our paper with Pablo and Alejandro is what they said at the beginning. And it's a statement saying that all sequential element rules, that they are not only Fisher and replacement monotonic, but they are also obviously strategic. They are not only strategic proof, but they are also obviously strategic. Perhaps the main part of the contribution is that we are able to show it in a constructive way. That is, for each sequential alignment rule, we construct an extensive form that will depend very much on the rule, because we want to implement the rule with the property that truth-telling in this game is obviously dominant. Yes? So the proof is constructive. And is constructing, we are using an algorithm. So we are using a general algorithm. I give just two properties. So the construction is in two tiers. The first tier, we propose general traits of this algorithm. Yes. At each of these steps, we select a player and an assignment for the player that can be interpreted as a guaranteed assignment. So select an agent and a number of units, and we say, okay, here you can just take this one, and you will receive the end. Yes. If the agent chooses this, he will not play anymore, and at the end will receive this amount. And then he gets into the set of what we call a stop agents, because they want to stop with this guaranteed amount. If he asks for more, represented with this plus, then the guarantee assignment might go up in 1 unit, perhaps later on. Yes, and he gets into the U and U set, the set of players that want to go up. Yes, he may play later on, or he may not. But in any case, if he plays, he will be in this set that they want to go up. And he asks for less, then he gets into this, and perhaps the next guaranteed assignment will decrease, but perhaps he will not play anymore. Yes. So just the plus and the minus, is this could be, this beta could be 0, could be k, just this will be denoting the maximum between -1 and 0, and this will be denoting the maximum of beta plus 1 and k. Yes? So if the process determinates before the agent leaves, then the agent gets his guaranteed assignment. Yeah? And now the guarantee assignments will evolve through the algorithm by assuring that all proposed guarantees are feasible. Yes? And those paths have to be monotonic, are specific to the agents, and that's what we call monotonous and individualized algorithm. Yes? The second tier is now how we choose this agent and the guaranteed assignment at any step of the algorithm. And the idea is we are going to use precisely the rule. The rule will tell me, so this MIA algorithm leaves open some of the selections of the pair of the agent and the guaranteed assignment. Now, this selection has to be a particular one once we have a rule that we want to implement in obviously dominant strategies. Yes. So fix now, just to give the example for individual rational rule, take a rule. Now suppose that is individual rational, so this is the case. So now this is the guaranteed alignment that will be used at the beginning, is Q. Now we start with an agent, and what we want is to classify the agents according to QI, whether they would like to get more, or they would like to get less, or they would like to get the valid one. So we do sequentially, we're offering to every agent this guaranteed allotment, and starting for agent 1, then agent 2, up to agent n. So the stage A consists just on, has as an objective, the classification of the agents according to whether they want more or less or equal amounts, units, with respect to the guaranteed allotment Q. Yes. So what they offer to them is precisely whether they want Q less or more. Yes. And depending on this choice, they get into the down, S, or up sets. Yes. So at the end of this stage A, what we got is a partition of the agents according to their wills with respect to this original guarantee allotment. Yes. So if one of these two sets is empty, then we stop, and the outcome is Q. Observe that in this case it means that this is efficient, so we stop. Otherwise, it means if the two sets are non-empty, now we go to stage B. And what does the stage B? The stage B does precisely the specific Pareto improvements that have to be carried out from Q by identifying the agent, one agent that wants more and an agent that wants less, and carrying the transfer of one unit among them. Yes. So stage B now have several steps. So that can be just the first step just after stage A, or stage B, BT-1 that comes from a previous stage B. Yes. So we choose these two agents, and now we are going to offer to them. So, and we are also carrying out the so far guaranteed allotment. Now what we are going to offer to the agent that is in up, an additional unit that the previous guaranteed allotment, and the agent that is in down, we are offering a guaranteed allotment that has one unit less than what he had just selected earlier. Yes.
I'm sorry, we have a little bit of a connection problem. I'm trying to reconnect.
Diego, it was almost over because he ran out of time. So if you want, the only thing I had to add here is I can finish just now if you wish. It's just a couple of minutes. It's just a couple of minutes.
So just give me 1 second and I should be.
But they can, if you want, it's not almost.
So Jordi, if you can take over now.
Yes. What it remains, what I was finishing by emphasizing, that the question is now how to select this agent that is in up and the agent that is in down in order to carry up Pareto improvement, because it may be many. And the point is that depending on which one we select, then we are going to implement one rule or the other. So the problem is that the selection has to be rule dependent. And what we do in the paper is just by looking at particular profiles of potential tops using these already guaranteed allotments and distributing the up and down agents between K or 0 to identify for sure an agent that at the end will have to receive exactly the guaranteed allotment plus 1. This will be the guy in up. And now using this guy, now we can look at that among the set of players that want to go up, down, and stay, identify a profile where now we can, there will be for sure an agent in down that will receive 1 unit less. And therefore, this is the Pareto improvement transfer that we'll have to take into account. And this depends on the rule, because another rule might select another agent in up and in the other agent in and down. And this is the main difficulty of the proof. To prove that in this general mechanism, even for non-individual rational rules, truth-telling is obviously dominant strategy is relatively simple, because after all, the agent is always facing the possibility of getting the guaranteed allotment or getting up or getting down or both. And so truth-telling is very easy to identify in this case. And also it's very simple to say that truth-telling is obviously dominant. The difficulty, this is the difficult part, is to show that indeed the mechanism that we are proposing, that is the general MIA, which is a general algorithm that leaves open who plays and what is the guaranteed allotment, when tailored by a specific rule, indeed induces the specific rule. That's a difficult, because means I have tried to explain that there are many rules, and so the rule is telling me how proceed in this selection. Yes, this is more difficult. And the individual rational case is relatively simple, because the stage A, which is the objective of partition the set of agents between the guys who want more or less or equal is very simple. Just offering the initial allotment. In the non-individual irrational case, this is a problem because we don't know which one is going to be used, the Q upper bar or the excess or the scarcity allotment, because we don't know the profile. So now if they are different, it means that somehow they both are allotments. So somehow we start with these two reference allotments, and what we are going to do by giving to some Asian initial guaranteed allotment, we are going to start a process that these references are going to move in this direction until they collapse. And once they are collapsed, now it's like being the individual rational case, which is the easy. So this is essential what I'm taking advantage because I think it was less minutes that in the tape that now I'm using, but so that's better. So that's it. Essentially, that's it. And in some sense, the main point means a surprising fact. The truth is, we were working in another setting with single P preference in the public good setting, and usually there are no obviously strategy proof, and there is a severe reduction of the set when there are. And this is somehow surprising because I think in this literature, although the notion is very strong, we are showing in a particular setting where the class of strategy proof is extremely large, that obviously strategy proof don't reduce a lot the class. So I think it's in some sense a surprising result. It's not in the literature. There are not many of these cases. So that's it, Diego. Yes.
Thank you, Jordi. Sorry about the technical problems at the end. The full video will be available for everybody on the YouTube channel, so you can watch the final part of Jordi's talk. But now let's move to some Q&A. If anybody wants to ask questions, either raise hand or let us know. Okay.
So you mentioned that there's in general, you have these rules where there's these two different endowments, a scarcity and excess one, and somehow you can start from both of them at the same time and move inward. Yes. And it seems miraculous that this doesn't screw up the obvious strategy proofness where you worry about the best case and the worst case. How does that work?
Yeah, because the only thing we have to, let me see what we have to do. So we know, so we have these two references, yes. So because this does not depend on the profile, we just look at what is, we have the rule, let's look at the image when everybody asks for 0, what is the allotment when everybody looks for K. And what we are going to do, because this, we could construct another way from the Q upper bar. We start from the Q lower bar. If they are different, it means that there is somebody whose Q lower bar is smaller. And now this is where we are going to start. So we are going to offer this guy this amount, yes, and let's see what happens, where he ends up, yes. And so we are going to keep doing this and show that indeed these two processes converges. The key point here is the identification of the new guaranteed allotment. Because once we are giving to an agent the guaranteed amount, now this should be guaranteed. And hence now we have to evaluate again the rule, but not at the extreme profiles, at the profiles where, for instance, the guys who had already said, I want this amount, the guaranteed amount, they are, the top is at this particular number of units, and then keep proceeding. This is, means the truth is that the proof is the hardest part of the proof is precisely to show that this process indeed converges, and not only that, that maintains the incentives of the agents of keep telling the truth along the process. But this part is done in the general setting. We know that any application of particular specification of the MIA, of the algorithm, truth telling will be an obvious strategy. The difficulty is that to show that precisely implements the particular rule that we start with.
Jordi, I'm Antonio.
Yes. Oh, hello. Nice meeting you. Nice to meet you.
So may I ask you, if I understood correctly, it's more qualification questions. The mechanism is a discrete version.
Yes.
But can you think about a continuous version of the mechanism? You fix the speed at which this distribution occurs, given the number of agents who are on one type of the other.
Yeah, this is something that I run out of time, but let me see. We started with the continuous case, although at the beginning, you observe, for instance, the sending clock version of the Birkeler-Groves mechanism that Lee has already in the paper. The other applications that when we started were also with the continuous. The difficult part of the notion of obvious strategy proofness is the identification of the earliest point of departure in the extensive form between two behavioral strategies. And if you think a little bit, this may not even behavioral strategies may not be well defined. Then we started, in fact, we started to look papers that are dealing with extensive for games where, in some sense, the stages, the time is a continuous one. And then we became very afraid of there is Carlos Alos, right? There are papers that deal with these issues, and that is extremely complicated. So we quickly moved to the discrete case, and we thought, okay, we will look at later, and the truth is we never done. But still, I think it's a difficult issue. But after all, I don't know. It's, units cannot be distributed in a continuous way. The difficulty here is not just for the units; it's for the timing of the sequential process. The revelation now is going to be through a period to a sequential process that takes time. And if this time is continuous, that means that now the steps in the algorithm, the nodes, are also continuous objects. And then the behavioral strategies in this setting may be difficult animals. Although there are results that you can deal with that, but we haven't done specifically. It's something that we thought we would do sometimes, but we never done. But it makes a lot of sense to ask how we could do it for this case. But this, I think, is a common feature of many of these papers that are studying now obviously strategy proof mechanisms. The discreteness of the time of the extensive for game.
Any other questions? No. So thank you, Jordi. So we can just unmute and give a round of applause to Jordi.
Thank you. Thank you.
So now we have a break. It's a long break right now from for about a little bit more than an hour. We're going to open some breakout rooms if people want to talk to each other and so on. Otherwise, we can continue here with the next talk by Pietro Ortoleva, one of the Social Choice and Welfare Prize winners. That will start in a little bit more than an hour from now. Okay.
Thank you. Hi, Diego. This is Arunava. Hi. Hi. It's muted. Hi. So you will. So Pietro and Ariel will be live. I mean, they will be. It must be very early there too, right? I mean, I can't hear you.
Hey, sorry, Arunava. So Pietro, I think will be joining a little bit once we start his video.
He will join.
He said he would make it for the Q&A session.
Excellent.
Also, Ariel will also be joining for the Q&A session. For them in New York right now, it's around 6 a.m. So they should be up in a few minutes.
I see. Okay.
We'll do the same thing. We'll play the video of the presentations, and if Pietro makes it, we'll have the Q&A. Otherwise, we'll just go to a quick break, and we'll have Q&A in the second transmissions.
Okay. Thanks for doing this, Diego. You didn't get to go to bed at all at night, it seems.
Well, I changed to Paris time, and I went to sleep early last evening, and I got up early, and it's all good.
Okay, thanks.
Okay,
Okay.
Arnava.
Okay.
Diego, ¿cómo vas?
Bien, Kanishka, ahorita ya estamos por empezar la siguiente sesión, creo.
Sí. ¿Cómo fueron los otros? ¿Había gente?
Sí, tuvimos como 60 participantes.
Jordi.
Apenado con Jordi, que ya llegó, porque tuvimos un pequeño problema en la sesión de Jordi y estoy apenadísimo todavía. Estás silenciado, Jordi.
No te preocupes, Diego. Faltaba muy poco y pude decir lo que faltaba, no hay problema. No te preocupes. Incluso mejor, porque tomé un poco más de tiempo. Sorry.
We should switch to English.
Yes, sorry.
No, I understand that. I'm watching Narcos, so I'm perfectly okay.
You understand Spanish, Arunava?
Entiendo todo.
Oh, very good. Hello, Kanishka.
Hola. Hey. Hey, Frosma.
Hey, Kanishka.
Hey, how are you?
Good. So
Oh, good place, huh? In the Golden Bridge. Yeah.
Yeah.
So are you in Mexico City?
Yeah. I'm in San Francisco. No.
Yeah, but it should be dark there. It should be dark there.
Yeah. So how is everything going, Francois?
Well, no, not bad for me. You know that the
Uh-huh.
country is doing terribly,
Yeah.
but I have a
But you're manufacturing the vaccine. I mean, you guys should get it before others.
They invited, but they are not the UK and using the American one. So the first ones have been UK, no, perhaps Russians. I don't know.
Yes,
Yeah.
Russian and
But
Chinese.
the UK are using the Pfizer, so the so
Yes.
not the Oxford.
No, not Oxford yet.
I'm already online, you know, in front of the hospital, just waiting.
Yeah.
It's a terrible life. Yes, you imagine that it didn't work. There are some virus that there are no vaccines. Imagine to know
But
that
you know,
this is our life for always. It would be terrible.
but there are no vaccines for HIV, but there are very
For
good
instance.
therapies, right? So there are all, I mean, everything, one thing or the other works.
Yeah, but it took many years to get it. So the therapy
It
took
took
many
several
years. Many people dying before. So
but the technology was, I mean, the state of medical technology, you know, by the time they sequenced the RNA sequence, it took several years. Here it was done.
okay. They're quicker. Yes, I understand that. But still, I don't know. I think the vaccine is much better.
Yeah. So Francois, I was just replying to you. You will get a message very soon.
Thanks.
Okay.
So you feel well, Arunava? Yeah. You feel, or you have some still?
No, I don't know. I mean,
What do you mean? What do you mean? You know so many things, and you don't know this one, which is so basic.
no, I mean, I feel fine. I just feel that there
Oh.
may be something that I cannot, that I'm not aware of, because one still hears of, it's a clotting problem. So I had very high clotting, in my blood,
Yeah.
there are things about their blood, this thing, it's called D-dimer and CPK protein or something. Those numbers were 3-4 times higher than they should. And I also had pneumonia. So I mean it was I mean, I didn't have breathing difficulties, thank goodness. I didn't have breathing difficulties.
You had to be okay.
I didn't have any this thing, but I went to hospital because I felt I was it might happen.
You had a lot of fever.
I had fever for more than 10 days. And then my results came positive, and psychologically it's terrible because you feel you're constantly thinking, am I going to get
yes, of course.
am I going to find it difficult to breathe and stuff like that? So I mean, so I did go there to hospital, but the doctors and all were kind of amazing. I mean, they all wear these suits, so you don't know who they are, but they work tirelessly, and they don't have any fear or anything like that. I mean, I cannot believe that that's perfect. And they wear it for like 7-8 hours. They cannot go to the bathroom. They cannot drink water. They're doing it day after day.
Okay, I guess we should start, no? It's Okay, welcome to this session, the prize lecture session. So as in all the sessions, you will have time to ask questions in the question and answer session. That is after the lecture. So we'll play 2 videos. So let me share the screen.
It's a great honor for me to introduce the winners of the Social Choice Prize for the year 2020. Pietro Ortoleva of Public and International Affairs, Princeton University. Earlier, he was a faculty member in the departments of economics at Columbia University and the California Institute of Technology. Pietro completed his laurea in economics at the University of Torino and his PhD at New York University. Pietro's main contributions are in behavioral economics, but within that field, his work is very broad. At its core is a desire to understand decision processes from multiple perspectives. A lot of his work is an elegant attempt at modeling well-documented empirical observations. He also uses the experimental method very effectively to develop deep insights about behavior. His early work studied the phenomenon of the status quo bias within a multiple priors framework and that of incomplete preferences under uncertainty. He has contributed to the literature on reference-dependent choice behavior, including the problem of endogenizing the reference point. In decision-making under risk, Pietro's work has helped us further understand behavior that is influenced by the certainty of effect, i.e. the decision maker's attraction towards risk-free prospects. His work has also shown us deep connections between the 2 most well-known and enduring paradoxes in decision theory, that of the Allais paradox and the Ellsberg paradox. In recent years, his work has looked both theoretically and experimentally into the phenomenon of decision makers demonstrating a preference for randomization. Pietro's work is important for social choice for several reasons. Some of it bridges behavioral economics and political economy, the latter essentially being positive social choice. This includes, for example, his work on overconfidence in politics. The connection between behavioral economics and social choice will only be further strengthened in the future. Most of Pietro's work is also founded on the axiomatic method. In both spirit and substance, it is intimately related to the methods of social choice. Finally, let me quote from his nomination statement. Pietro is amongst the most impressive economists of his generation and certainly at the very top in the behavioral economics field. His research touches on so many areas and important questions that it is impossible to design a syllabus in decision theory without repeatedly referring to his work. Congratulations again, Pietro.
Hello, everybody. My name is Pietro Ortoleva, and I am, it's a pleasure to be here, and I am presenting today a paper that is my new work with Simona Cerea-Vioglio and David Dillenberger that is called Caution and Reference Effects. So let me share some slides. What is the basic idea of this paper? That essentially what we want to do is to try to give a new spin using the idea of caution to understand a variety of different behavioral phenomena that thus far has been typically modeled using different means. So let me illustrate. Sorry. So consider the following 4 big items that I would claim are at the core of behavioral economics. The endowment effect, which is the fact that people tend to value more objects once they're in their possession than when they're not. Present bias, the fact that people violate exponential discounting by discounting more to the present. Loss aversion, which can be understood as an asymmetry in the valuation gains and losses that manifests itself in the rejection of symmetric bets. And the certainty effect, which is the violations of expected utility in the direction of liking certainty. Now, if you're not familiar with these, I'm going to remind you what they are a little bit more slowly later. But the fundamental idea and the point I want to get across is that these are 4 of the big items at the core of behavioral economics. Typically, if you look at the class in behavioral economics, every class includes these 4 items, plus typically, other regarding preferences. And these are probably the most characteristic elements of a behavioral economics class these days. Of course, there's many models that try to address them. And some of these are fantastically popular for good reasons. One of them is the model of cumulative prospect theory, of course, of Kahneman and Tversky, that is built on 2 pillars. There are 2 main pillars to explain this behavior. One pillar is a conceptual idea, which is the idea that losses loom larger than gains. That is that the way we suffer from a loss is more pronounced than the happiness we get from a gain of an equal magnitude. Right? So there is a fundamental asymmetry in our treatment of gains and losses. And cumulative prospect theory uses this to explain loss aversion and the endowment effect. On the other hand, the other pillar of cumulative prospect theory is probability weighting, which is the idea that decision makers don't use probabilities for what they are, but in their evaluation, they weight probabilities based on some on some psychological factor. And this is used to explain the certainty factor. So this is cumulative prospect theory. To explain present bias, there are many models. One of the most well-known ones is the beta-delta model that essentially says that agents have a non-exponential discounting in that they discount future to future using essentially exponential, but when it comes to discounting to the present, there is an extra element, the beta in the beta-delta model, that leads us to present bias. So these are not the only papers. There are hundreds of papers about this phenomena, but by far the most popular ones. What do we do here? Here, what we're going to try to do is that we're going to instead suggest a novel, unified approach. And it's going to be built on the idea that our decision maker doesn't know which utility they should use. And not knowing what to do, they act with caution in deciding, in deciding their action. I'm going to show you that this story, the fact that you don't know your utility and you act with caution, the 2 elements together generate, in a model, all the 4 phenomena above. So the first contribution is that we're going to give you a story that generates all of these. We're going to try to do something a little bit more ambitious. I'm going to present to you a result. Limited time is not going to allow me to explain everything, but I'm going to present at least hint to some result that shows how this behavior can be formally connected, in the sense that we're going to argue that you can understand both the endowment effect and present bias and loss aversion as manifestation of a special type of multidimensional certainty effect. So I'm going to connect them precisely. This model will be an extension of our previous work of a paper called Cautious Respect Utility that me, Simon, and David published in 2015. But of course, it's going to extend it, and then it's going to show this new phenomenon. This was a paper that studied the certainty effect. Now we're going to take a similar model and show how this maps into the endowment effect, loss aversion, present bias. Crucially, I will try to argue that our approach is conceptually and behavioral different from existing models, meaning not only we give a different story, but also we can capture behaviors that existing models cannot capture, and vice versa. In fact, I will show that our model is completely distinct from a cumulative prospect. And finally, this distinction, I will argue, is going to be useful to organize some of the existing evidence. So I will try to convince you that our approach is useful to understand some of the data that we have. This is where we are. So before I tell you how we study this phenomena, let me just briefly remind you of what these phenomena are. The first phenomenon we want to study is the certainty effect, which is the violation of expected utility in the direction of overvaluing risk-free alternative or certain alternative. The most famous example is probably the Allais common ratio effect, which, according to which agents are asked to choose between 3,000 for sure and 4,000 with probability 0.8, 0 otherwise. And in this case, they choose 3,000 for sure. And the choice between 3,000 for sure, 3,000 probability 25%, 0 otherwise, and 4,000 probability 0.2. And in this case, they choose D. And this pattern, choosing A here and D here, is incompatible with expected utility because, as you can probably see, C is nothing but A mixed with 0, probability 75%, and D is nothing but B mixed with 0, probability 75%, which means that under expected utility, because of the independence axiom, connected to the independence axiom, A better than B if and only if C better than D. So we have a violation of expected utility in the direction of like uncertainty. What is the endowment effect? The endowment effect, instead of something unrelated to risk, is the observation that is made famous in the famous Kahneman-Nash-Taylor Muggs experiment, in which so the famous experiment goes as follows. Subjects are divided in two groups. One of these two groups is given a mug. They can look at it, and then they have to decide how much money they want to sell it. You know, this is the willingness to accept, the minimum amount of money they are willing to accept to let go of this mug. A second group is instead offered to examine the same mugs and ask how much money they would be willing to pay for this mug. And the critical finding is that the willingness to pay for people who don't have the mug is typically lower, significantly lower, than the willingness to accept of people who do own the mug, essentially going against the idea that there is a unique value of this object. Loss aversion. The third phenomenon is loss aversion. Now, loss aversion is used in many ways in the literature. Here, I'm going to understand it as the idea of rejection of symmetric bets. That is, suppose that I ask you, do you want X with probably 1/2, or minus X, or minus X with probably 1/2, or do you prefer 0? That is not to bet. Do you accept this bet? And most people, the loss aversion is the observation that most people prefer 0. So it's a rejection of symmetric bets, which of course is nothing but a form of risk aversion around 0, but that has specific meaning because it says that our treatment of gains and losses has some nature of asymmetry of some type. And finally, completely different, a different setup, a different environment, present bias. What is present bias? Is the observation that decision makers don't follow exponential discounting, but overemphasize the present. In particular, our decision maker may be indifferent between y at time tau and x at times tau plus t. So going from y to x compensates for the extra period. But when we move it to 0, so when the starting point is 0, now they prefer the 0 payment, which is something that is impossible with exponential discounting as a violation of stationarity, but it is the idea of present bias. Now, what I want you to look at is that these four phenomena are very different things. Two of them have to do with risk, although one is about risk for gains, the other one is about the symmetry of risk, gains, and loss. One is about buying and selling objects that are not necessarily risky, so conceptually unrelated to risk. Another one has to do with intertemporal allocation, that is completely unrelated, on paper unrelated. So the question is that, is there a way to see these phenomena in a unified lens and capture them as stemming from a same sort of conceptual intuition? So this is how we're going to address the problem with a model that is called cautious utility. That is, let me define the setup. The space I'm going to operate in, I'm going to think about a world in which we have a compact set A that lives in Rk, where K is a multi-commodity space. So think about each dimension as representing money today, or mugs, or pens, or money tomorrow. For example, if I want to think about intertemporal choice, I can think about each dimension as a date. So I can think about money today, money tomorrow, money in 3 years, and so on. Or if I'm thinking about buying and selling, I can think about one dimension as being mugs, the other one money. Now, for now, I'm gonna keep dimension 1 to represent money today. And the objects I want to study is a complete and transitive preference relation over lotteries over A. Okay, so what I'm doing is that I'm studying preference over lotteries over these bundles. Again, nothing standard. This is, I'm taking Econ 101 setup and I'm putting lotteries on it. Let me just remind you of a bit of notation that, of course, you're all familiar with. If EI denotes a normal vector, zeros everywhere except one in dimension I, and if X is a scalar, then XEI is nothing but the vector. It is 0 everywhere except X at dimension Y, X dimension I. So in this context, I can define the cautious utility model. And let me go somewhat slowly here, because this model is the core of is the model we're going to operate. So to define it, the first thing I'm going to need is that I'm going to need a notion of monetary equivalence. Let me define them. I'm going to say that if V is a utility function, I'm going to define, and P is a lottery over these bundles, I'm going to define the monetary equivalence by CPV, which is the amount Z, such that the utility of getting Z dollars, that is Z of dimension 1, which is money, remember dimension 1 is money, is the same utility of that lottery. So the monetary equivalent is the amount of dollars that makes you indifferent with the lottery if you have utility. Now, given this, I can define my model, which is the cautious utility model, that says that my decision maker has not one utility, but a set of utilities. And they evaluate a lottery over these bundles by doing the following. For each utility, they compute the monetary equivalent, and then they pick the smallest one of these to make their evaluation. Now, what is the logic here? Well, this model has two fundamental tenets. One is the fact that the agent has multiple utilities, and the other is that the agent is using caution to select. So the idea that the agent uses multiple utilities, you can think about it this way. Suppose that my agent is evaluating these bundles. The agent may be unsure of how to aggregate this. The agent may look at the board and says, well, I don't know how to evaluate what is the right trade-off between money and mugs. I'm not sure. I'm going to entertain multiple ones. Okay, so that's something the agent can do. Now, the model says the agent entertains a bunch of these utilities. And, of course, once you have multiple utilities, how do you make a choice? How do you, which one do you use? The model says, use the most pessimistic one. Use caution. That is, use the utility that gives you the smallest value. And this is the second tenet. So, tenet number 1, multiple utilities. Tenet number 2, caution in using them. Now notice, you may look at this and say, yeah, but why using the monetary equivalence? Why don't we have the info of the expected utility? Why aren't we just doing that? Why mapping into this monetary equivalence? And there's a reason, and the reason is the following. Think about it for a second. Suppose we didn't do the monetary equivalence. Suppose that here we just did the inf of the certainty equivalent, of the expected utility. Then what would we be doing? We would be making a comparison across utilities. But when you were a child, your grandma told you never to make comparison across utilities. Utilities are designed to make comparison within utilities. Comparison across utilities are subject to all sorts of concerns, normalizations, units and so on. the most kosher way of approaching the problem is to bring everything down to the same unit of measure, which is, in our case, monetary amounts. And this is what we're doing. Now, this model already, as I write it, you can probably see that gives rises to the certainty effect. That this may lead to non-expected utility behavior in the direction of the certainty effect. And I know it. Why? Because this model is an extension to a multi-commodity space of a previous model that me, David, and Simone published in 2015, is the one I was telling you about, called cautious expected utility. There we only thought about monetary lotteries, not lotteries over bundle, and we defined the equivalent model. We showed that this model can generate a certainty effect. Intuitively, this is the case because this model, in this model, the monetary equivalent of a sure amount of money is always that sure amount of money, so the inf doesn't matter. Okay, now let me briefly tell you why do we think this model is interesting and where is this model coming from, and this is going to be important. I'm going to show you that this model is characterized by an axiom that captures the certainty effect. So I'm going to ask you to consider the following axiom, negative certainty independence, which is a generalization of an axiom that my co-author David introduced in a 2010 paper. And it's the following idea. My decision maker, so the starting point is the independence axiom that says that P is better than Q if and only if P remains better than Q even after I mix them with other items. Now here, what I want to do is that I want to generalize the independence axiom by allowing for the certainty effect. Well, here's one way to do it, to just say that at the very least, an independence-like property should hold whenever I'm looking at a lottery that is better than a sure amount. So let's see. What we're saying here is that, look, suppose that I have P that is better than, what is this? A sure amount of money, right? This is the general lottery gives me X dollars for sure. Now my agent likes sure amounts, and in this case, he's saying, well, I prefer a sure amount, but in this case, this lottery is better than the sure amount. So this lottery got to be pretty good. Well, if it was pretty good when compared with the sure amount, it must remain pretty good after I mix everything. Because after I mix it, what happens is that the sure amount may no longer be sure. So it's maybe losing its certainty appeal. We would claim that this axiom captures exactly the idea of certainty bias and of the certainty effect. In fact, it's deeply related to the definition of certainty effect given by Kahneman-Tversky. And what you can prove, and what we show in the paper, is that together with some basic axiom, transitivities, continuities, monotonicity, this kind of stuff, this axiom gives us the cautious utility model. And the opposite axiom, which is where I flip everything, gives us the anti-cautious utility model, which is the equivalent model with a bunch of utility, but with a soup. This is not too surprising because it's an extension of this is extending our 2015 result. So now I'm going to show you how this model in the multi-commodity space can generate an endowment effect and loss aversion. Let me define these things. I'm going to say that an agent is loss averse if they prefer 0 for sure to a lottery pays X or minus X with a equal probability, loss seeking otherwise. And then I can also define a willingness to pay and a willingness to accept of a certain amount of a certain item. I'm going to say that the willingness to pay is the amount that makes you indifferent between 0 and getting M units of that item, I, and foregoing a certain number of units of item 1, which is money. So this is what I get to do when I sell. While a willingness to accept is the minimum you're willing to accept to sell M units of item I, which means that is the amount that makes you indifferent between letting go of M units of item I and acquiring a certain amount of units of item 1, which is money. And of course, what I want to show is that WTI is bigger than WTP because that's endowment. Now, how is the commodity prospect theory studying these problems? By assuming that utility functions that are asymmetric and that losses loom larger gains. Here instead, I would like to stay neutral. And I would like to keep some symmetry. I'm going to show you that I can do it even preserving neutrality. And how am I going to do it? I'm going to think about, here's the way I'm going to define it. I'm going to, for any function, I can define the conjugate of this function, the symmetric reflection of this function as the function that is f bar as minus f equal to minus f of minus x. And I'm going to call a function odd if it's equal to f bar. What does it mean? A function is odd whenever it's symmetric around 0. That is, whenever I take the projection around 0, it remains symmetric. Why is it called odd? Because power functions with an odd exponent are odd. Then I'm going to say that what I'm going to assume is that, remember here I have a set of utilities. I'm going to assume that my set is odd, by which I mean that either every function in the set is odd, or that if I have a function that is not odd, that is asymmetric, the opposite asymmetry is there. That is, as a whole, my set maintains, if I have ever deviate in one direction, I will deviate in the other direction. But if you want, for now, you can think about every function there being odd, which is something we can give behavioral foundation to. And now the key result I want us to, build all of this up to get to is the following proposition. Give me the cautious utility model with an odd set, then this model will be exhibit the endowment effect and loss aversion. While if you give me the anti-caution, again maintaining the odd set, then this model is going to generate the opposite of the endowment effect and the opposite of loss aversion. That is what I'm showing you, is that even if you give me quite a bit of symmetry, if we are neutral about the symmetry, if you have multiple utilities and you take the inflow, you have caution, you get the endowment effect and loss aversion. While if you do the opposite, you get the opposite. And conceptually, I want you to see that this is showing that under some assumptions of symmetry, this is showing that because the cautious utility model is characterized by the certainty effect in the appropriate space, is telling us that if I impose the certainty effect, I get the endowment effect and loss aversion. And if I impose the opposite, I get the opposite. So it's proving how these behaviors are related. And for us to understand it, let me go through an example, which at the end of the day is the core of the paper. If you understand this example, essentially the theorem or the proposition shows that this example is generic. And the way I want you to think about this world is that think about a world in which I have two dimensions that are money and mugs. So I have just two dimensions. Now remember, the core of the model is that you have a set of utilities. And here I'm thinking about the simplest stuff I can write. Again, nothing special about this, it's just simple. Utility of money and mugs is the number of money, amount of money plus the mugs, or amount of money plus twice the number of mugs. These are two basic utilities, the simplest I can write. Notice that both utilities are completely symmetric, there's nothing special about gains and losses, but these utilities are different in that they entail a different trade-off between money and mugs. Because according to the first utility, one mug is equal to $1. According to the second utility, one mug is $2. This is going to drive everything. So let's see. Let's compute the WTP and the WTA. Suppose I do the WTP. Well, what is the WTP? Is the amount Z that makes me different between 0 and minus ZM. But the value of 0 is 0. Well, the value of minus ZM is what? Well, it's the minimum of the values for each of the utilities, which is either minus Z plus M or minus Z plus 2M. But now, look, which one of the smallest? Well, of course, if M is positive, it's minus Z plus M. So to get the value of Z, I set it equal to 0 because I need the indifference. And so I get that the WTP is equal to M. Conversely, suppose I do the WTA. I have zeros indifferent to R minus M, right? Because now I'm acquiring R dollars and letting go of M units. I do the same trick, but now these numbers are R minus M and R minus 2M. And the key observation is that, of course, now which one is smaller? Now it's R minus 2M, which means that WTA is equal to 2M, which means that the WTA is equal to 2M, which is strictly bigger than the WTP, which is the endowment effect. Now, what is going on? Let me tell you a story. The story is my agent doesn't know what is the right trade-off between money and mugs, either $1 or $2 per mug. Now, not only the agent doesn't know the trade-off, but the agent is also pessimistic. He's acting with caution. So let's think about it. When you're selling, what are you worried about? You're worried that you're selling something that is actually very good, not for the right amount of money. So when you're selling, which trade-off do you use? Well, the one for which the money is the best object. So you want a lot of money. So you want 2M. Instead, when you're buying, what are you worried about? What you're worried about is that you're buying an object that is not really valuable. Therefore, if you're cautious, which utility are you using? The one with the lowest trade-off, just $1. Hence, the endowment effect. Now, I want to claim that this approach is different from the cumulative prospect theory approach because it's coming from not knowing what is the right exchange with objects and applying caution. And we claim that this helps us organize the evidence of the endowment effect, which is according to which the endowment effect tends to be stronger for objects that agents are less familiar with. Now, I'm not going to have time because we're almost out of time, but you can probably start seeing that the similar logic is going to give you loss aversion. And you can imagine a similar logic giving you present bias with a decision maker who is unsure about how to aggregate things intertemporally, because maybe my decision maker may be unsure of what the utility function is going to be next period. My agent may be unsure about that. And what we do in the paper is that we also show that this model is not only different as a story, but there's no intersection with the cumulative prospect theory model. Now, of course, this paper is not unrelated to, it's related to a lot of literature. I didn't have time, but of course, we're standing on a lot of shoulders here. We build up on a lot on the literature of, especially on incomplete preferences that relates to many of these behavior. The big difference that we have with much of this literature is that we use the notion of caution. So just to conclude, what do we do in this paper? We have a novel approach to study biases in which the agent doesn't, these biases in which the agent doesn't know which utility to use and acts with caution. We have one story, that is the story that generates the sorted effect, loss aversion, endowment effect, present bias, not only generates all of these, but connects them formally and conceptually. This is a model that is distinct from existing models and that we think helps organize existing evidence. So thank you very much for listening and very much looking forward to the discussion. Bye-bye.
Kanishka, am I audible? Yeah. Hi, Pietro, are you there?
I am. Hi.
Hi, I'm Arunava. Congratulations.
Thank you. Thank you very much.
And well, thank you for waking up very early. Very interesting talk. So if anybody would like to ask Pietro a question.
I have a question. Do you hear me?
Yeah.
Thank you for this very interesting talk. I'm wondering if you have some opinion about the normative appeal of this way of reasoning for an agent having multiple utility functions, because you talked mainly, I think, about descriptive observations and the fact that this model can fit these descriptive observations. Now, it seems to me that possibly it is also more normative as an argument in favor of it. It could be perhaps more normatively appealing than prospect theory for the following reason. Once I have chosen, so if I assume I have a set of utility functions in mind, then when I'm forced to make a choice because I need to sell a mug or buy a mug, I pick one of these V and then assume, this is not in your model, but we could go on and say, assume that I will now stick to it. So I collapse my set of utility functions to one, and now I stick to it. And then I avoid money pump problems and these kind of things that are possible with prospect theory. Have you thought about these kinds of defense of this approach?
So that's a very good question. To be honest, we have not thought about it. We have not thought about the normative dimension. Let me give you my gut reaction to the issue. I think it's an important question that we should think about. So in terms of money pumps, that's right. Although one thing about the prospect theory, the endowment that it gives you is that it really stops you from having money pumps, however you want to generate it, right? Because the whole point of the willingness of the gap is that once you are in a position to then start sell it, you want enough money. It's very hard to exploit. Now, as a model, though, I think there is suppose I want to take a fully normative approach, like I have to teach people how to make decisions, like a corporation how to make decisions or a government how to make decisions. I think that this is so I have the impression that having multiple utilities may be, so suppose that you're a corporation or you're a government and you hear multiple people giving you advices. There are multiple experts, multiple subcommissions that come up with a rule of how to make this judgment. One thing you can do is that you could aggregate them in some way, and come up with one utility function. Another way that we're suggesting is don't aggregate, just keep it as is and apply a sort of minimizing loss sort of approach. Which is a discussion approach. As we're showing, these two leads to different places. You cannot replicate caution as if you were creating a utility function. And it's not entirely obvious to me, what is the right approach that the government should take, depending on the goals of the government, right? If you're a politician and you need to have a defensible position, for example, a cautious approach could be easier to defend towards scrutiny than other, there are, so I'm always very scared with normative because I barely understand what people do, let alone what they should do. So as you can see, I put all the caution additions I can, but I think, I think that's something we should be looking into because it's something that, I always thought that the approach of multi-utility and incomplete preferences has a normative resonance, that arguing that normatively, we must always come up with one, econ 101 kind of preference is not entirely obvious. So thank you.
Thank you.
Other questions? So let me ask you a sort of very naive question from the viewpoint of sort of social choice. So when you do these sort of aggregations and so on, I mean, for social choice, you have multiple cells, you have multiple, whatever Bernoullians, utility functions, and then you're taking the minimum. So I mean, these social choice theorists are sort of quite used to sort of aggregating, these are not cells, but these are actual people and then you aggregate, and then there are certain axioms, and there are sort of two sort of primary things. One is some average, some utilitarian, weighted utilitarian, and the other one is the sort of Rawlsian max-min, which is like the thing that you do. There's one major difference between these two things in social. I mean, you guys are creating the individuals with the preferences, right? I mean, there is no a priori, number of agents, and then you're trying to aggregate. But I'm just sort of curious as to what sort of axioms that you get in order to get the sort of cautiousness, the minimum aspect of it, rather than some average of it, which is also, you see it over and over again. There's some sort of invariance axioms which will, I suppose the nature of the invariance axiom which will give you either the line or the L shape or something.
Yeah,
it's a very naive question.
No, it's a very interesting point, and to the point that we started exploring it a little bit more formally, the connection with social choice. And I know the one is possible because they have a student, Lasse Manonen, who's on the market this year, and he has a paper in which he does a multi-utility version, and then he has an application to social choice about the comparison of fairness of societies using his approach. So he studied state-dependent utilities. So I know a mathematical connection can be made, so we are exploring it, but to answer your question, I think, so there are two differences. One, of course, is a difference in story. We have multiple selves, and we start from the behavior of one individual. From the behavior, from this preference, which is a complete preference, we derive a bunch of utilities. And then we represent them with multiple utilities, and then we take the aggregation. So the difference is that we start from one person and then we derive the multiple selves behaviorally. But that's a matter of where you start from. There's a different story, and there's another difference which maybe sounds irrelevant, but it does matter quite a bit. And it is the fact that in our multi-comparison, you take the cautious approach, meaning you take the smallest, but you take the smallest of the certainty equivalents. You don't take the smallest of the utils, right? So it's not a Rawlsian approach in that you're doing really the L shape, because you convert everything in certainty equivalents, which is an approach that of course has been used in some ways in various bits in the literature, in studying intertemporal preferences, but it's rather uncommon in the application. The way this is emerging is all driven, so the key axiom is this negative certainty independence axiom that essentially is built on the following idea. It says that, let me remind you briefly of the axiom, if a lottery is better than a sure amount, after you mix them, the ranking preserves. So this is implied by independence. So it's a weakening of independence, but it allows for violations of it. Now, first of all, if it was as powerful as independence, it would bring us back to a linear aggregation, because of course independence is affinity, and affinity is linear, is a linear aggregation in this context. So everything would fall down. Now, it doesn't bring us there because this axiom is weaker, because it only imposes that if a lottery is better than a sure amount, then if I mix them, they remain, this ranking is preserved. But it doesn't say anything about what happens when I'm comparing lottery with lottery, or more importantly here, a sure amount with lottery. So why does it lead us to caution? Let's try to understand it. First of all, conceptually, when you have lottery versus sure amount, what this is telling me is, for an agent who is particularly biased in favor of the sure amount, if I start from observing that the lottery is better than the sure amount, it must mean that this sure amount, this lottery must be very, very good, right? Because it's beating even a sure amount. Now, suppose that I mix it with another lottery. Now, what happens is that the sure amount may no longer be sure. So the appeal of the sure amount may disappear. And now the lottery, which was already good to begin with, surely will remain better after the mixture. If instead I started from a sure amount and a lottery, so if I have a sure amount that is better than a lottery and I mix them, now what happens is that it may be that the sure amount was better than the lottery, but after the mixture, the sure amount is no longer sure. Therefore, it may lose its appeal. Now, once you're here, let me rephrase everything in terms of social choice. The appropriate way of seeing it, and it's a parallel that has been made in literature on ambiguity, is to map the sure amount to a completely even distribution in the society, so it gives everybody the same amount, and a lottery is an uneven distribution. And then what this is telling me in terms of an axiom of social choice is to say the following: suppose that that an uneven distribution is preferred to an even one. Now, if I mix them both with another distribution, this ranking would be preserved. Now, if you take exactly this idea, this is the high-level connection. Now, what is, it's going to give you a caution-like representation for the distribution. Now, I'm replying for something that we haven't formalized, so I don't know exactly what it would map into, but I think that's what I would.
Okay. Yeah. Thank you. Thank you. Thank you. Any other questions? Kanishka, how are we doing for time?
Yes, we are doing fine, right? We still have some time to take some more questions.
Is there time for a question from Paris?
Yeah. Please.
Yeah. Okay. So thank you very much. This was a very nice talk, and congratulations again to the prize. So towards the beginning, you were illustrating the idea of taking this minimum, but not of the utilities, but of the monetary equivalence. And you were trying to justify why are we going to the monetary equivalence. And you were saying, well, we all got taught when we were children never to make comparisons. And so I just want to try to understand what you mean. So are you wanting to say that initially we have an intuition, don't compare across people, and now we are doing this kind of idea, we apply it to intra-self comparisons. Don't compare among your different normative intuitions, among your different desires, so to say. Relatedly, is it not the case that through this move towards the monetary equivalence, what we are doing is not so much that we avoid a comparison, but rather that we actually make possible a comparison by choosing a joint normalization, by moving to a kind of correct common normalization of our different normative intuitions?
Yes. Absolutely. So in fact, this is what I meant to say. So let me phrase it like this. So what I meant to say is the following, that, the phrase in the talk was a joke, but the problem is that, so what I meant to say is that it's hard to make comparisons for different utilities, especially if you using the same different utilities for the same person, because you need some degree of normalization, right? So if you take a person with one utility and you compare it with another utility, and then you don't do any form of correction for normalization or bringing everything to the same unit of measure, these comparisons can be highly misleading. Because of course, if I normalize things differently, I can remove everything. Now the question is that how do you normalize really? Because you can say, okay, these are expected utilities, so I have 2 degrees of freedom, I can fix the top and the bottom. But then the problem is that this is not obviously the right, mapping. And exactly as you're saying, the way we understand what we're doing in doing the certainty equivalent is exactly trying to bring everything in the same unit of measure, where the comparisons are meaningful. So literally, the way I would say it, even the way I teach it when I teach it, is that this is a normalization that is quote unquote the right normalization. So I really agree with you that this is all that we're trying to do, is to normalize in the most complete sense, because what we're doing is that we're bringing to the same unit of measure.
That clarifies it. Thank you.
A short question following up on that. Is it true that if you go to the certainty equivalent for any good, the representation will still work, or does it depend on which good you select?
Okay, so we could have rewritten it. Absolutely. So so you have to readapt things. So it's not the same. Things may change in the sense of it's not the same behavior you can explain, and I can, so let me phrase it like this. So certainly you can generate everything I showed you, like loss aversion and the certainty and the endowment effect and so on, by just changing the certain equivalent to any good you want. So that would follow trivially. Trivially, no, but we did check, and it does follow. And in a way, that's because, as maybe your intuition is already suggesting, it's just a matter of where you take them in. But it's essentially, for example, if you recall the example of the endowment effect there was due to the uncertainty about the trade-off. And at the end of the day, the uncertainty about the trade-off is independent of whether I'm then normalizing the certainty equivalent with respect to money or with respect to MOGs. So that really doesn't matter. Where it might matter what you take the certainty equivalent about is if you have, because having the certainty equivalent in one direction, in the time dimension, it might matter. So once you do the time application, which I haven't discussed, but there it might matter that you want to have, you must take the certainty equivalent to be in a specific dimension and not in an intra-dimensional certainty equivalent. So there are ways in which you have to be careful there. I'm being a bit vague because it's a word of caution of an application I haven't showed you. So but yeah. But thank you. Yeah, it's a fair point. I should have actually mentioned it during the talk.
Hi. Any more questions?
Yeah, perhaps.
Yeah, Hans.
Yeah, perhaps just a very simple question. So I did some applications of loss aversion. That was the simplest version of loss aversion. So you have an expected utility function. Players have a reference point, and then below the reference point, you downscale your utilities in a linear way. What's interesting in the applications, at least what I found interesting, is that the reference point is determined by what players in the game do. Okay, so my question is this now a very special case of your model, or is it really different? Or can you apply your model to the situation so that it becomes a special case?
Right, so that's a good question. So let me phrase it like this. Because our model subsumes expected utility, and because the standard model, the way you were describing the application of a loss aversion, which is expected utility with a utility function which is not symmetric around zero, is subsumed by expected utility, by the transitivity of nesting, it's a special case of our model. Almost in a trivial way, right? Because we allow for everything there. But I would like to make a point that is slightly more subtle, which is the following. That what we show in the example and what we show in the paper is this, that loss aversion gets there by having one utility which is asymmetric. Now, suppose that instead of having one utility that is asymmetric, I have multiple utilities, and I impose that this set of utilities is odd. Then I can also explain loss aversion, but that way of modeling is no longer nesting the standard model. So now you get the same behavioral dynamic of people disliking losses, but our model no longer is a generalization of that model. So let me just repeat. In general, our model as an umbrella encompasses the standard expect utility with loss aversion. Not prospect theory in general, but expect utility with loss aversion, yes. But once you impose an odd set of utilities, our model goes to a different branch. We no longer get standard loss aversion as a special case, but yet we can get a behavior like loss aversion, but with a model that is different, that is going to have different implications. So, but you can, then you can generate reference points endogenous in the same way you generate them with loss aversion. Admittedly, the model is less simple to operate with. The beauty of the loss aversion model, which is why I used it in my own. I have 2 papers that use the standard loss aversion model. The beauty of it is its extreme simplicity. So for applications for a strategic situation, which are complex by their own right, they provide a simple modification. We think that our modification may have other points of interest. In particular, we think we can capture some behaviors that the standard loss aversion model cannot capture. But indeed, they're not. Once you impose odd, they're no longer nested.
Okay, thanks.
Okay, so I think we're out of time, Kanishka. So please join me in thanking Pietro and congratulations again. Okay, thanks. So Kanishka, what happens now?
Yeah, we stay here for in 2 minutes. We'll start the next session.
Okay.
Okay, so let's start the next session. Again, for who joined later, we'll have question answer sessions after the talk. So for 15 minutes. So you will have time to ask questions. Let me share the screen.
a great honor for me to introduce the winners of the Social Choice Prize for the year 2020. Ariel Procaccia is Gordon McKay Professor of Computer Science at Harvard University. Before joining Harvard, he was a faculty member in the Computer Science Department at Carnegie Mellon University. He completed his BSc and PhD from the Hebrew University of Jerusalem. Ariel is a computer scientist whose research has opened new areas in normative economics. His early work in computational social choice is highly impressive. He was a co-editor of and contributor to the 2016 Handbook of Computational Social Choice. He's, however, best known for his path-breaking work, both theoretical and practical, on fair division. Theoretically, he has shown how the classic solutions invented for distributing indivisible commodities in the Arrow-Debreu model can be adapted to the important environment with indivisible objects. Let me just mention two of his contributions. He has proved that the Buddhist concept of max-min share is not always feasible. On the other hand, the maximization of the Nash product retains the no-envy property in an approximate sense. In terms of practice, Ariel has launched two non-profit websites that turn the abstract solutions identified in the formal literature into practical tools for decision-making and fair division. The Split It website, launched in November 2014, has had thousands of visitors who enjoy its user-friendly approach to iconic fair division problems. The site applies a variety of concepts from the Shapley value to the competitive equilibrium with equal incomes. Users of the site can also propose new division problems, which has in turn led to new theoretical work by Ariel and his students on the allocation of classrooms in the LA Unified School District. Let me also mention Ariel's recent work on liquid democracy, on gerrymandering, and on statistical approaches to voting, which have opened new directions for social choice. So let me end by quoting from his nomination statement. He's a deep mathematician with an uncanny instinct for turning theoretical results into concrete methods for solving real-world problems. This is a mixture of talents that is significantly improving the reach of several key models in the field of social choice and welfare. Congratulations, Ariel. Thank you.
Hello, my name is Ariel Procaccia. I am delighted and honored to give one of two Social Choice and Welfare Prize talks this year. The topic of the talk is democracy and the pursuit of randomness. Let me give a shout out to my collaborators, Gerdos Benade from Boston University, Bailey Flanagan, Paul Gueltz, and Anupam Gupta from Carnegie Mellon University, and Brett Hennig from the Sortition Foundation. I want to start with a quote from Jean-Jacques Rousseau, who had this to say about early democracy in England in the 18th century. He said that the people of England deceive themselves when they fancy they are free. They are so, in fact, during the election of members of parliament, for as soon as a new one is elected, they are again in chains and are nothing. So this is, of course, a very dramatic quote, but I think it still captures the sentiment that some of us still have, around engagement and participation in democracy today. But of course, the question is there a different way of doing democracy? Is there an alternative? One intriguing answer to this question is the idea of sortition, which is the idea of democracy built on lotteries instead of elections. Or in other words, the idea of choosing representatives at random instead of through an election. Now, this may sound crazy, but it actually has a lot of historical precedent. The idea dates back to ancient Athens, where some of the most prominent bodies of government, including the all-important Council of 500, were chosen through sortition at random. In the Renaissance, in Florence, in Venice, and the Kingdom of Aragon, sortition was very prevalent, and again, some of the most important bodies of government were chosen through sortition. But sortition all but disappeared during the American and French revolutions that built these new democracies around the idea of elections and essentially made democracy synonymous with elections. However, in the last couple of decades, sortition has really seen a resurgence in the form of citizens' assemblies, which are randomly selected assemblies consisting of everyday citizens. They're often commissioned by local or national governments, and the goal is for these people to deliberate and reach decisions on important questions and inform policymakers with their ideas. Now, this has been happening on a wide scale in recent years. Let me just give you one example, or like 4 examples out of hundreds. So one kind of very visible example is a constitutional assembly that took place in Ireland in 2016 with 99 participants. The assembly was followed by a national referendum that itself led to changes in the constitution. So this was seen as a very big success story for sortition and citizens' assemblies. In France last year, the president sponsored a very visible climate assembly to discuss climate change with 150 participants. In Mongolia in 2017, they had an assembly consisting of 669 participants to talk about the constitution. And in South Australia, they had a 50-person assembly to talk about nuclear waste in 2016. But again, these are just 4 examples out of hundreds. I'll give you later 2 more examples of assemblies where our methods played a role in selecting the participants. So how is sortition done? Ideally, the pipeline for sortition would be choosing the panel directly from the population at random, either uniformly at random or, even better, using stratified sampling, which means partitioning the population into groups and choosing a fixed number of people from each group in order to get a panel that is guaranteed to be representative of the population. However, this is not how things typically work in practice. In practice, you have the population, of course, but to reach out, sortition organizations usually send out letters at random, inviting people to serve on the panel. We've been in touch in the last couple of days with an organization that is reaching out to people by phone and doing random digit dialing, but typically it's done with letters by mail. Now, some of the people who receive a letter opt in and agree to potentially serve on a panel, and they then join the pool of volunteers. And then the final step is that we want to randomly select a panel from the pool of volunteers. Now, the challenge is that the group of letter recipients is representative of the population, and we want the panel to be representative of the population, but the pool of volunteers is highly unrepresentative of the population. Let me illustrate this with an example that will also show you what I mean by representation here. So this is based on data from Climate Assembly UK, a national UK climate assembly that was organized a couple of months ago. It was sponsored by the UK House of Commons, so it was a government-sponsored assembly, and it was run by the Sortition Foundation. The participant selection part was done by the Sortition Foundation using the methods that we'll talk about later. Now here, 60,000 letters were sent. The size of the pool, the number of volunteers, was 1,727. We'll denote that by N and note how small this is compared to 60,000. This is typical. And then the panel size that we denote by K is 110. Now, there are 7 features that the organizers cared about in terms of getting a representative pool. So these are gender, age, geography, education, ethnicity, area, which is urban versus rural, and position on climate change. And what I'm showing you here in these pie charts is the distribution of the feature in the population compared to the pool. So if you look at area, for example, urban versus rural, you can see that the pool is actually quite representative of the population. The proportions are roughly the same. But look at education. The most highly educated people in green are much more common in the pool than in the population. And correspondingly, the people with the lowest level of education in blue are much more common in the population than in the pool. Similarly, if you look at position in climate change, the options here are very concerned about climate change, fairly concerned, not very concerned, or not at all concerned. And you can see that the people who are not very concerned or not at all concerned in green and red have good representation in the population, but are almost not represented at all in the pool, which is not surprising. If you're not concerned about climate change, it's highly unlikely you would volunteer to serve on the climate change panel. So, with this in mind, the problem is the following. We want to select a panel that is representative of the population at random from a pool of volunteers that is highly unrepresentative of the population. How do we do this? So this is something that sortation organizations and practitioners have struggled with. And essentially all of them have invariably come up with some kind of greedy algorithm. Greedy algorithm is computer science terminology for an algorithm that is myopic in the sense that it does at every stage the best thing right now without looking into the future. So I want to show you a particular greedy algorithm that was the one previously used by the Sortation Foundation, but this one is pretty representative. The input to the algorithm on the left is the set of volunteers that in the STOI example are identified by two features, shape, star or heart, and color, blue or green. So we have 20 volunteers. We have a panel size of 10, k equals 10. And finally, we have quotas, which are meant to ensure that the panel is representative of the population. So in this example, the quotas are, we want at least 4 stars, 4 hearts, 4 blue people, and 4 green people. Now, the way the algorithm works is at every stage, it identifies the feature value with the highest need, where the need is defined by the ratio between the quota that remains to be filled and the number of remaining volunteers in the pool with that feature value. And then once it identified the highest need feature value, the algorithm chooses uniformly at random among the remaining volunteers who satisfy this feature value. So let's see how the algorithm works on an example. Initially, we compute the need for each feature value. So for star, it's 4 over 10 because the quota is 4. We have 10 stars in the pool. Similarly for heart. For blue, it's 4 over 11. And for green, it's 4 over 9. We have a quota of 4 and 9 green people in the pool. So the highest need is for green. So what I'll do is I'll choose uniformly at random among the 9 green people. And I chose this green star that's highlighted in yellow on the right. Now, at this point, what I have to do is recalculate the need for each feature value, in particular, recalculate the need for green and star. So now the need for green will be 3 over 9. We need 3 more. We have 9 stars remaining in our pool. And the need for green is 3 over 8. We have 3 people that we still need to choose that are green, and 8 green people remaining in our pool. But at this point, the highest need is actually for heart with 4 over 10. So I'll go ahead and select a heart uniformly at random from the pool on the right. And so I chose the heart. I now need to update the need for each feature value. I get these updated numbers. If you look at them, you see that now the highest need is for green. So I'm again going to choose a green person uniformly at random, update the needs. Now the highest need is again for heart. We choose a heart uniformly at random. And again, highest need is green, and highest need is heart, and then green, and then heart. At this point, we've selected 8 people according to the algorithm. And at this point, we still have 2 seats to fill, but the quotas have been filled. So we have 4 stars, 4 hearts, 4 blue people, 4 green people. We can choose the remaining 2 people on the panel uniformly at random. But the thing to notice is that until this last stage, the blue star, the one blue star we have in our pool of volunteers, had no chance of being selected because the algorithm alternated, remember, between green heart, green heart, green heart, green heart. So evidently, the blue star has a much lower probability of selection than the other volunteers, which seems unfair. Now, you might say, maybe this is something that's inherent to this example because of how the quotas are built. And we'll see in a couple of minutes that this is not the case. Now, you might also wonder, maybe this is just this toy example they have carefully constructed to make the greedy algorithm look bad. Maybe this doesn't happen on real-world examples. But this is, again, not the case. It very much happens. So let's go back to our our Climate Assembly UK data. And what I'm showing here is the histogram of selection probabilities for volunteers, for the 1,727 volunteers that you get when you run the algorithm on this data set. So the thing to notice here is that if you look at the bar at the far left, these are the volunteers with very, very low probability of selection, very close to zero. And you can see that many of the volunteers, around 450, are in that category, are given very low probability of selection by the greedy algorithm. Now, you might again say, maybe this example is such that the quotas forced you to give really low selection probabilities to volunteers. But that's again not the case. So here's a different algorithm that I'll refer to for now as a mystery challenger. I'll unmask it in a couple of minutes. When you run this other algorithm on the same data set, you get the histogram at the bottom, where you can see that everybody is getting a fair chance. Even the minimum probability is kind of bounded away from zero. So everybody has a reasonable probability of being selected. So this tells us that the greedy algorithm is kind of unfair. We're going to revisit this point later. But for now, the question is, how do we get from the histogram at the top to the histogram at the bottom? The key idea is the idea of looking at distributions over panels. So if we go back to our toy example, remember that I promised you that there is a better way of dealing with this example. And the idea is that with probability 1/2, I'm going to choose a panel that consists of the top row of volunteers and the third row of volunteers. And with probability 1/2, I'll choose the second row and the fourth row. Now notice that each of these panels ex post satisfies the quotas. There are at least 4 stars, 4 hearts, 4 blue people, and 4 green people. Moreover, these two panels together, their union is the entire set of volunteers. So by randomly selecting between them with probability 1/2 each, I guarantee every volunteer a selection probability of exactly 1/2. I'm able to exactly equalize the probabilities. So this is intuitively the fairest thing you can do and the right thing to do on this example. Now let's spice things up a bit and increase some of the quotas. So we'll raise the quota for star to 6, heart is still 4, blue is going to be 5, and green is going to be 5. The thing to notice about these quotas is that they force me to choose a blue star. Because if I choose 6 stars that are not blue, they're all going to be green, then I need to choose 4 more people for my panel, among the hearts, but that won't allow me to fulfill the quota of 5 blue people. So I have to choose the blue star. But still, under this constraint, I still have a lot of flexibility. So what I propose is that together with the blue star, I'll choose 5 green stars uniformly at random and 4 blue hearts uniformly at random among the 10 blue hearts. So this gives me a distribution over many panels, where each one of them is chosen with probability 0.00003. However, the selection probability of each volunteer is actually very high. The most unfortunate volunteers are the blue hearts, and even they have 40% probability of being selected because every time I select 4 blue hearts at random among the 10 blue hearts. So what we saw here is that by eyeballing these simple examples, we can kind of come up with intuitively fair outcomes, intuitively fair distributions over feasible panels. But of course, we want a more general principled method of doing this. And in order to do that, we're going to draw on a beautiful area that's very close to my heart called fair division. It's a sub-area of mathematics, economics, computer science, political science, and it deals with how to fairly divide stuff according to rigorous notions of fairness. In our case, the thing that we want to divide is selection probability. So what we get is that a distribution over panels of size k divides the overall selection probability of k for the k seats on our panel between the pool members. And we kind of think of the utility of each pool member as their selection probability. With this in mind, we can now use some of the tools and ideas developed in fair division in our sortation problem. So this will now allow me to unveil our mystery challenger. It's an algorithm, a mechanism called Lexamen from the fair division literature that's known to have great properties in some applications. In our setting, what Leximin does is it will choose a distribution over feasible panels that maximizes the minimum probability of any volunteer being selected. Subject to that, there could be multiple distributions achieving this. It maximizes the second lowest probability, then the third lowest, and so on. So in other words, it tries to push the lowest probability of anybody as high as possible. Then when it got stuck, it pushes the second lowest probability as high as possible and the third lowest, and so on. When you run this on the Climate Assembly UK data, you get the histogram that we saw before. Now, another option from fair division is called maximum Nash welfare. What it will do in our context is it will maximize the product of selection probabilities of the volunteers. This intuitively, also kind of tries to equalize probabilities, but it shoots for a smoother distribution over probabilities. So if you look at the histogram, you can see that things look a bit smoother than Leximin. It's also a bit misleading because it may seem that Nash welfare is doing better on the Leximin objective than Leximin itself, right? Because the lowest bucket has fewer people, more people are pushed to the right. But this is misleading. In fact, the minimum probability under Nash welfare is lower than Leximin. They're just in the same bucket. So Nash welfare essentially sacrifices the lowest probability in order to get a smoother distribution over probabilities. So focusing on Leximin, I want to revisit this idea of being fair in terms of the worst off people, giving everybody a fair chance, and taking an even broader viewpoint. Because so far when we looked at real data, I showed you this one data set, but you might be again suspicious and say, maybe greedy looks bad on this one data set, maybe things are different on other data sets. So again, this is very far from being the case. At this point, we've collected 8 different data sets from citizens' assemblies from 4 different organizations, 5 from the Sortition Foundation, 1 from Off By For All, 1 from Healthy Democracy, and 1 from the Center for Climate Assemblies. And what I'm showing here is for each one of these data sets, the purple bar is showing K over N for calibration. So this is the panel size divided by the number of volunteers and gives us the idealized selection probability if we could exactly equalize probabilities, if we could choose uniformly at random. Now in yellow and green, I'm showing the minimum selection probability of any volunteer under Leximin and greedy. And what you can see by looking at Leximin, the yellow bars, is that Leximin always gives everybody a fair chance. In many cases, it's even comparable to what you could get if you had no constraints. The greedy bars in green are essentially invisible. And what this says is that under greedy, in each one of these data sets, some volunteers have almost no chance of being selected. So this is really a general phenomenon. Now, another thing worth noting is that these algorithms, in particular Leximin, are very difficult to implement. Computing them is a hard computational problem in a formal sense. And we have quite a bit of theory around an algorithmic framework for computing them, and also some non-trivial engineering tricks to make it happen. But at this point, we've been able to implement these algorithms, and that's led to an open source system called Panelot, which stands for Panel Selection by Lot at random. What it does is it takes as input the pool of volunteers, the quotas, and the size of the panel, and it outputs the Leximin distribution over feasible panels. Now, this system has been available for roughly half a year now, and it's been used by a bunch of organizations around the world. So in particular, this whole collaboration started from our work with the Sortition Foundation based in the UK. The co-founder and director of the Sortition Foundation, Brett Hennig, is a very close collaborator and a co-author on the paper that I'll mention in a few minutes. The Sortition Foundations are the ones that did participant selection for the Climate Assembly UK, and they used Panelot for that purpose. Now, in the last couple of weeks, we've been in touch with an organization in Germany called Nexus that is organizing a visible assembly there, and they have already decided to use Panelot. This will happen in the next couple of weeks. We've also been in close touch with organizations in Poland and Canada, the Center for Climate Assemblies and Mass LBP, mainly at the level of data sharing at this point. And finally, in the US, we've been working with a whole bunch of organizations. One that I want to mention in particular is called Off By For All. They've used Panelot in order to select participants for an assembly that happened in Michigan in September to talk about COVID-19 policy. And what's been really exceptional about how they used Panelot is they put a lot of thought into how to select a single panel from the distribution given by Panelot in a way that is transparent, in a way that encourages trust in the system. So they came up with some great ideas. And in particular, the selection itself, they live streamed it and they recorded it. And what I want to show you is 1 minute from that video in which the presenter explains how they use Panelot in order to very transparently choose a single panel.
So what we set out to do, and what we have done, is sent out invitations to 10,000 randomly selected households across Michigan. Once those of you who were willing and able RSVP'd to us, a volunteer team of computer scientists from Carnegie Mellon University as well as Harvard used an open source algorithm that they developed to generate a list of 1,000 possible panels. Each one of these has a different mix of 30 citizens who again reflect the makeup of Michigan with those proper proportions, women and men, young, old, etc. Now, each of these possible panels is identified now by a unique number, 000 through 999. The three machines that I have here with me, each will select just one digit of that 3-digit number. Together, that will give us a 3-digit number, and that will be the group of 30 that has been chosen to serve as the panel.
Okay, so let me wrap up with a take-home message, which I think kind of represents this work on sortition, but more broadly represents some of the stuff I've been really excited about in the last couple of years. And it's that computer science and math have a role to play in improving the practice of democracy and potentially in shaping its future. I think this is especially pertinent for the social choice audience for whom this talk is intended. There's so much beautiful theoretical work in social choice. Of course, some of it has been applied, but I think especially now there are so many exciting opportunities to take all of this theory and really put it into practice and influence the trajectory of democracy. This is something I really believe in and something that's really inspired a lot of my own work in recent years. Let me finish with the bibliography. So the work that I talked about is based on a paper with Bailey Flanagan, Paul Gueltz, Anupam Gupta, and Brett Hennig called Fair Selection of Citizens' Assemblies. We are finishing up the write-up of the paper, so it's not available yet. It should be available in the next 2 weeks or so. In the meantime, I want to mention 2 more papers that play a role in the full version of this talk, but I didn't have time to talk about in the 30-minute version. One is a paper called No Stratification Without Representation that thinks about the more idealized sortition pipeline that I talked about initially, where you can choose directly from the population. If you can do that, what's the right way of doing that? The second is a paper called Neutralizing Self-Selection Bias and Sampling for Sortition. This takes a slightly different view of fairness, where instead of being fair to the volunteers, we want to be fair to the population itself. So it's an end-to-end view of what being fair in terms of selection probabilities really means. I'm going to end with that. Thank you so much for your attention.
So thank you, Ariel. Very nice, wonderful talk, and congratulations again. And if somebody would like to ask a question, please go ahead.
Yes. So I followed the French Citizen Climate Assembly, and there is many people talking about the question of bad representation, with the argument that volunteers, because they are volunteers, are different from other people. I never spotted a question about the kind of technicalities, if I understand, that you can solve with this algorithm. So I would like to know to what practical defect in these assemblies you are correcting, in fact. What is the real problem? I understand in theory the fairness issue, but in practice, have you had complaints about that, or what?
Yeah, so I think there are a couple of different interesting points here. So you raised the point of the volunteers not being representative of the population. So of course, one worry is that if you don't do the selection in a way that is principled, you might get a pool that is not representative of the population. So you might get a panel that is not representative. The quotas are supposed to kind of address that to some degree. But I think there's beyond the quotas themselves that are dealing with individual feature values, there's also the issue of different profiles of people. So in the example that I gave, if we thought about these blue stars that had no chance of being selected, that is something that is corrected in the greedy algorithm. In our algorithm. Now, I think beyond that, there's also this issue of, the question is, what is the purpose of randomness in sortition? So our view is that part of the purpose of randomness is to guarantee fairness in a way that, just gives people the impression that they are able to participate if they so choose, and that nobody has a special mandate to serve on the panel. So that, this is something where there is an impression where if you don't do this in a way that is random in a principled way, then you might not get this positive effect of randomness that says, this is really a true chance to participate and be represented. So this is something that came up in discussions with practitioners, and part of what we're trying to correct by kind of really making the selection principled.
Other questions?
I have another question. An issue with these patterns of selecting people through quotas is that you do not in practice looked at cross quotas. Okay, so you try to fill them one by one, but maybe they are correlated. Okay, so have you some ideas about that, or how to? First, is this really an important problem in practice, and can you fix it?
Yeah, so we have looked at this. The method that I talked about, doesn't directly try to address this issue, although I think it does to some degree. We have another paper that I mentioned at the end of the talk that looks explicitly at all possible, types of people that are defined by vectors of features, and looks at being representative in those terms. So let me give you some preliminary answers. The easy case is when, if you're in the idealized setting that I talked about at some point where you directly select from the population, I just mentioned this briefly, then you can just divide the population into the different types and kind of do stratified sampling, and that you select the correct number of people from each type. So that is an easy case. The problem in practice, if you want to be truly representative of all types of people, is that the number of types is much larger than your pool of volunteers. So if you think about the UK Climate Assembly or the French Climate Assembly for that matter, you might have around 10,000 types, but the number of volunteers is on the order of 1,000. So some types won't even be represented in the pool of volunteers.
So one way to kind of treat this formally is to say, here's the expected number of people that should be selected from each type in proportion to their size in the population. And what we would like to do is to choose a distribution over feasible panels whose vector of expected seats to each type is as close as possible to this perfect representation in terms of, for example, Euclidean distance, right? So every distribution will give you a vector, and you can look at that objective as one example. So that is actually an objective that we can optimize in our framework. So we have this algorithmic framework that in particular can optimize and practice Lexem and Nash welfare, but this objective also fits into that framework. So if you really want to put a high weight on representation of kind of intersections of features, then this is one approach you could take that is feasible and somewhat different from the one that we have implemented in practice.
I guess Vikram has one question there.
I have a question. So,
please.
Oh, somebody else has a question? Okay, Vikram?
No, go ahead, Felix, go ahead.
Okay, thank you. Well, first off, Ariel, congratulations for receiving the prize. Very well deserved, and thanks for the very clear presentation. The question I have is a very general question about sortition and also applies to quotas. So how is it decided which criteria or features are actually relevant? So in your examples, things like gender, ethnicity, age seem reasonable, but need not be. Somebody else might also consider things like height, weight, or hair color or something which doesn't seem reasonable at all. And this might be quite important. How is this problem addressed in general?
Yeah, so the specification of the features is, on a technical level outside of our framework, this is something that's decided by the organizers. But let me, it is a very interesting point which we have actually thought about. So in particular, we have a paper in EC19 that thinks exactly about this question. It isn't this idealized pipeline of selecting directly from the population. And essentially the question it asks is, if we did have the possibility of doing this kind of stratified sampling, where we're given the vector, we're given like features and types of people according to some criteria predetermined, and we've stratified over them to make sure we're representative. But now there's a different feature that we haven't stratified over, which can be, like you said, Felix, height or weight, or it can be, I think, it can be a sensitive feature that we couldn't stratify over. It could be a political position that we just didn't have information in order to take into account. Is it possible that we're doing badly in terms of this hidden feature when we stratify over features that, explicitly stratify over given features? And what we found is that at least in that setting, you actually are not doing worse compared to uniform sampling when you stratify over features that are not the feature that you're now worried about. So for any hidden feature, if you look at the variance of the number of people selected with that feature, the variance will be at most as high up to some small error as what you would get if you did uniform sampling from the population. And in some cases, it will be much lower if this hidden feature is well correlated with the features you stratify over. So, this is just one particular example in a setting, but at least in some settings, it's something that is on a technical level, something that isn't too much of concern in the type of stratification that you want to do, in the type of techniques that we would use to get representation. Yeah, so hopefully that answers the question. I mean, maybe to say one more thing beyond that, when the organizers choose their feature, the features, they're the ones ultimately responsible for justifying and defending the assembly. So they will choose the features in a way that when people then ask, is this really representative? Like when I look at the pictures of all of the people on the panel, is this really representative of the population? They will have to justify and say, yes, it is. So obviously there is quite a bit of pressure on the organizers to spend thought thinking about which features would end up giving something that they can then defend as representative. So that would be kind of the more conceptual part of the answer.
I see, thanks, yes. So, but actually a related problem is also that for some features, people may actually lie about them. So there's a truthfulness issue. So like maybe for things like age, this is not really a concern because you can look it up somewhere. But political position, for instance, it might be something that is also something that people might...
Right, I mean, that's a great point. And if you think about the climate assembly data, for example, so there, I briefly mentioned this, in position on climate change, if you're not at all concerned, if I remember correctly, there are only 4 people in the pool out of the 1,727 that said they're not at all concerned. And these people basically had to be deterministically selected for the panel in order to satisfy their proportional quota. So it's absolutely true that if you said, I don't care about climate change, but I volunteer to be on a panel, then you would basically guarantee being selected in that case. It's a problem that we briefly thought about. I would imagine that there's an impossibility result, that you can't really deal with this without some kind of verification, but it might be something to look in more deeply.
Okay, so Ariel, there is a question from Vikram Manjunath on the chat, and he says, wouldn't the only way to address the issue that volunteering inherently makes you different from everyone else be to make panels more like juries? In other words, you draft people rather than have them volunteer.
Yeah, so that's very interesting. So I think that, of course, would be one solution, but we actually have a paper that I mentioned at the very end of the talk that deals with exactly this problem. So the way we think about it is that people have a probability, a self-selection probability of accepting an invitation once they're invited. And this probability is determined by their features. So, we saw, for example, that highly educated people are much more likely to volunteer than people with a lower level of education and so on. So we assume that you can predict a person's probability of opting in based on their features. And once you have those probabilities, you can reverse them at the panel selection stage. So when you have your pool of volunteers, you essentially select a panel with probability, if somebody's probability is QI, you select them with probability proportional to 1 over QI. So you have, when you now look at the whole pipeline, it starts with uniformly random sending of letters, and then self-selection probabilities and reversing of those probabilities. What you get is that the end-to-end probabilities of a person from the population being selected, for the panel are roughly K over N, where again, this is kind of what you would get if you could choose uniformly at random from the population. So we have a whole paper kind of building this idea. There are a couple of complications. The one on the theoretical level is you kind of need your pools to be to be kind of what you would expect in order to correctly reverse the probabilities, and we have some theory about that. The second obstacle is that you have to be able to predict the self-selection probabilities, and we have a significant machine learning component in this paper, showing that that is possible. So we have some nice techniques. I don't want to go into the complications, but it's not a trivial problem, and we are able to, I think, make a compelling case that we can predict these self-selection probabilities. So, it's kind of a long-winded answer, but the bottom line is that I think by reversing the self-selection probabilities at the panel selection step, it's just a completely different way of being able to deal with self-selection bias.
So just to add to this question, have you thought about applying this to jury selection? Because not having representative juries is actually a huge problem. So for jury trials, racial disparity is a huge issue, and it's kind of a similar problem.
It is. So, juries are often given as like an example of the last vestige of sortition that survived, before citizens' assemblies became very popular in the last couple of decades. I think on a practical level, jury selection, just like with the legal framework we have right now, is quite problematic because the goal really isn't, or the way it kind of works in practice, nobody cares about representation. So first of all, People can in the US, as you may know, people can kind of shirk their duty pretty easily. If they don't feel like going, they can make some excuse. Whereas people who are not as busy at work, for example, may have less of an incentive to not do their jury duty. Another issue is that lawyers kind of select among the candidates for jury duty in a way that has nothing to do with the presentation. And it has more to do with who they think would be more susceptible to the kind of arguments they want to make, more sympathetic to the defendant or to the prosecution and so on. So, I think on an idealized level, the problem is essentially a problem of sortition. And if you look at like ancient Athenian democracy, that's kind of, I think, the model that they had in mind. Like you basically select from the population, things like the Council of 500. But I think, it's just like on a practical level, with all of the legal complications we have right now and all of the legal scaffolding around jury duties, I don't feel like these techniques would be kind of practical.
Okay, thank you, Ariel. I suppose we should close the session now. So congratulations again, and let me thank you again for your talk and for the prize. Thank you.
Thank you.
Je te dois toujours 3 euros.
But how to give the price now?
Yeah. Yeah, that's
I think that will have to be done by mail.
Yeah, that's Vincent. Vincent is sending me.
Okay, maybe I can say something briefly.
Oh, Vincent, yes.
I have a problem with the medals. Okay,
okay.
I have to apologize to the winners because there used to be a firm that used to issue medals in France, and I was buying my medals there, and this firm is no longer producing the medals. So I have to find a new provider of the medals. So I hope that by Mexico, I will be able in the future to find new producer of medals and send them to Ariel and all the winners. So it's sorry for that, but I hope I find a solution at one point.
Thank you. No worries, of course.
Thank you very much. So Kanishka, we wait for a bit.
Yeah, we can wait. Only like 10 minutes, and then we start the next session.
Dann miteinander ein wenig streiten.
Okay, welcome everybody. I guess we should start the next session. Yeah, let's wait for a minute so that everybody comes back. Okay, so it's our pleasure to have Leeat Yariv, who will deliver the Condorcet lecture this year. Leeat is Reinhardt Professor of Economics and the Director of the Experimental Lab for the Social Choice Lab for the Social Sciences at Princeton University. Her academic achievements have been enormous. She is the Fellow of the Econometric Society and a member of the American Academy of Arts and Sciences. Leeat is the lead editor of AG Micro and an advisory editor of Games and Economic Behavior. She recently has been associate editor of Econometrica, Quantitative Economics, and Economic Journal, and editorial board member of AER and Journal of Economic Literature. After finishing her PhD at Harvard in 2001, she has taught at UCLA and Caltech before joining Princeton. So now we'll play the video of Leeat. So as usual, you will have question answer with Leeat after the talk. Okay.
Welcome, everyone, and thanks for tuning in. So I'm going to tell you about a project with my colleague John Ergen titled Retrospective Search, Exploration, and Ambition on Uncharted Terrain. The observation that motivated this project is that good findings often follow a process of search. If you think about research and development, even your own work, you often develop techniques that feed into the future techniques that you think about, and so on and so forth. And at some point, you decide to write a paper. Policy experimentation has similar features where politicians or government officials try out new policies that often are incremental variations on previous policies. They need to decide how big of an increment, but at some point they need to decide what to actually implement. Mineral prospecting has similar features where often teams of geologists dig in various tracts of land trying to find various minerals. And as they do so in a certain area, they need to decide when to stop and declare a certain well promising enough to do future research with or digging. And online shopping has very similar features as well. So often you look for some item, say a widget on your favorite online platform, then you see reviews that direct you to future items. You need to decide how many of these to follow. And as you go through this process, at some point you decide to stop and pick your favorite object. So there are two features of all of these examples that we notice. The first one is correlations. So over time across samples, there is a link between observations. So innovation begets innovation. The second feature is that search scope is a choice. So how broadly or how ambitiously one searches through these processes is a matter of decision. So the main questions that guide us in this project are really trying to understand how such processes evolve. So how ambitious should search be given the observation so far, and when to stop? Now you might be wondering why I'm talking about this in a social choice and welfare gathering. So let me go back to one of our forefathers and my own personal hero, Marquis de Condorcet. And provide you with two sites that I think will link very nicely to our project. So the first one is one of Condorcet's more famous quotes, which says that truth belongs to those who seek it. So clearly he was thinking about search. The second one really speaks to this idea of correlated observation. So what Condorcet said is that as the mind learns to understand more complicated combinations of ideas, simpler formulas soon reduce their complexity. So again, the discovery begets discovery, and things build upon previous observations or explorations. So the main components in the model that I'll tell you about today are the following. So we're going to have a model of what we call a retrospective searcher. And this retrospective searcher faces correlated outcomes that we're going to model by thinking about a path that's governed by Brownian motion. And this will really allow us to think about innovations that beget innovations, or, for example, online reviews that suggest related products, or discoveries that suggest related discoveries, and so on and so forth. The other important component that a retrospective searcher will be allowed to choose is the search scope. So at any point in time, the way we're going to think about it is that our searcher is allowed to choose the variance of the Brownian path that they're facing. And this variance will come at a cost. And the last component that's shared in all of these examples is that of perfect recall. So once search has been terminated, our retrospective searcher enjoys the value from the optimal alternative that she inspected thus far. Now, here are the main insight that I'll try to convey to you in the next 25 minutes or so. So first of all, in terms of the optimal search policy, I'll try to argue that the optimal thing to do is to use a constant search scope. So in other words, regardless of the maximum observed or how promising the current values that you see are, you're always going to search at a constant, steady rate. The other observation that we have about the optimal stopping rule is that there's a stopping boundary that has a very simple formula that governs when the agent actually terminates her search. Now, this characterization of the optimal search policy will allow us naturally to identify the values of such search, but also to show you that it's amenable to various applications. And today I'll focus on one particular application, which is a principal agent relationship, and we'll focus on contracts that are very common both in the literature and in application, those of commission contracts that entail a fixed wage and a commission rate or a fraction of the final proceeds of the project. And we'll be able to characterize fully the optimal contract and also show you the agency cost in such contracts in particular cases. Specifically in the linear cost case, it's about 11%. All right, so let me immediately jump into the model. So the search environment is the following. We're going to have search that's conducted in continuous time, and correlations are going to be captured by a Brownian path, as I suggested already. So at any time t, our agent is going to observe the process x sub t And X sub t follows this simple standard Brownian path with variance sigma t, or standard deviation sigma t, that I'll soon describe where this is, and I'll soon describe where this is coming from. Now, the starting point x0 is exogenously given, and for today, we'll assume that x0 equals to 0. This sort of way of modeling correlation over time is really inspired by Callender in 2011, who also thought about experimenting with various policies and modeled the correlation in much the same way. Now, at any point in time t, our agent is going to choose the search scope, or the standard deviation sigma t. We're going to assume that the search scope is taken from a bounded interval. And furthermore, the minimal search scope possible, we're going to assume that it's strictly positive. And the reason why we do this is that we want the agent to either search or stop searching, but not just sit around idling and waiting for extended periods of time without anything happening. So in particular, we're going to assume that the cost of search is strictly positive, regardless of what search scope is chosen. So even if the minimal one is chosen, and it's also well behaved. So it's twice continuously differentiable, and it will be convenient, although it's not necessary to assume that it's log convex. So it's important to note that search here is costly. The more time you wait, you have to exert some level of effort through the search scope, and that's costly. Now, I already said that we're going to assume perfect recall, and that's because in most of the applications, that's what we think is the reasonable assumption. So what this means is that at any point in time t, the agent keeps track of the maximum observation that she's seen so far. So this is just the maximum over all of the observation that she saw up to time t. And the initial maximum M0 is exogenously given because we assume that the initial value of the process itself is 0. We're going to continue assuming that the initial maximum that's observed is 0 as well. So the agent's objective is going to be to maximize the expectation of the final maximum. That's her reward from the search, the maximal value that she observes throughout the span of the search, minus the overall cost that she spends, which is just the integral of the flow costs over time. So the agent has two types of decisions. The first one is how ambitiously to search at any time t. In other words, what is her search scope at any time t, or this standard deviation sigma sub t, and when to stop and gain her maximum. Now, some remarks on assumptions before I go to the analysis. So you may have noticed that we're assuming here a driftless process. So we're doing so mostly because we think this is what's relevant for many of the applications in hand. If you had drift, this means that a searcher just sitting around doing nothing would gain simply by the passage of time. So outcomes would improve only because time has passed, and that doesn't seem very reasonable to us. However, if you have fixed drift, you will still have similar qualitative results. We'll still have a fixed search scope, which will follow very much in line of what I'll show you next. But the stopping boundary that the optimal policy will entail will be somewhat different. Now, you could also imagine controlling the drift rather than the variance. Then it's a very simple trade-off that governs this decision. So we think it's not that interesting technically, and it's also not the relevant thing to look at for the applications we're interested in. Discounting is an important one. So in our model, the search is costly only through these flow costs that are linked to the search scope. If you allowed for discounting, much of the analysis would follow in the same lines. The search scope would still remain constant for the same arguments that I'll show you in a few minutes. The stopping rule would be a little bit more cumbersome to describe, so that's why we're not using it in our benchmark model. Risk aversion will lead us to very similar claims. So the search scope, even in the presence of risk aversion, remains constant. In fact, it's unchanged if you allow for for concavity of the utility. But the stopping rule is harder to characterize, and that's something that's actually very interesting mathematically. And if I had more time, I would describe to you what happens with risk aversion. So feel free to ask me in the Q&A session. All right, so with that in hand, I'm going to start to characterize the optimal search. So as I already mentioned, the strategy is composed of two elements: the choice of search scope at any point in time. This is the sigma t, or the standard deviation of the Brownian path, and the stopping time tau. And in principle, both may depend on the past realizations of both the maximum that you observe and the value of the project that you observe, as well as calendar time. Our first observation pertains to how agents stop in our model. So notice that at any time t with an observed maximum of m sub t, if it's optimal to stop at some value x sub t, it's also going to stop at the worst value x prime of t. So if it's even less optimistic right now, you're certainly more inclined to stop. So this suggests that there's going to be a stopping boundary that depends on the maximum observed that's going to govern when you decide to stop and just collect the maximum you observe. So you stop at t only if the current observation is sufficiently unpromising. So it's sufficiently lower than our stopping boundary. The stopping time is the first time at which you hit the stopping boundary. Now let me show it to you in a picture of what this actually means. So on the left here, you see a fairly simple stopping boundary, which corresponds, this should be a 45-degree line. So this just corresponds to a fixed distance from the maximum. It's as if we took the maximum and we deducted from it a fixed distance. Now, how does this play out with our process? Well, in the gray line on the right panel here, you see a caricature of our process x sub t. As that process increases, the maximum increases, and therefore the stopping boundary becomes more demanding. So it increases as well. And in phases in which the maximum doesn't change, because for instance, the process actually generates lower observations, the maximum remains constant, and therefore the stopping boundary remains constant. And then it continues going up whenever the process goes up, remains constant whenever the process remains constant. And finally, our agent stops whenever the process hits the stopping boundary, which in this picture occurs over here. All right, so the first claim that I'll show you is more technical in nature, but it will be at the heart of what allows us to simplify this problem dramatically. So in principle, this is a two-dimensional process. At every time t, you have to keep track of the maximum you observed up to now, mt, and the current observed value, x sub t. Now, proposition 1 tells us that at any time t, an infinitesimal change in the search scope, or the control sigma t, has no effect on the current maximum m sub t. And furthermore, and this is perhaps the more important thing for our purposes, sigma, the optimal control here, which in principle depends on the time and the full path of observed maxima and values of the process, can be described as a function only of the current observation. So this reduces the problem dimensionality dramatically because the optimal control depends only on the current observation. For those of you who are familiar with this literature, a technical intuition might be useful. So the control here, or our search scope sigma t, is adapted. And therefore, standard techniques allow us to write it as a Markovian control. And this, for this, you can use Bismuth or Gyeonggi and various other sources. Let me describe it to you through a picture. So imagine this process that's depicted through the orange line here. And suppose we're at the endpoint over here where the maximum was observed earlier on and corresponds to this point that is attached to the green horizontal line. So if you think about a small change here, an infinitesimal change here, it's not going to affect the maximum that's this distance away. And that's really at the heart of this. Now, you might worry of what happens when xt is exactly coincides with the maximum. Well, because we're in continuous time, you can be exactly at the maximum only for a 0 interval of time. So in a hand-waving fashion here, really this is the relevant case to consider. All right, so our simplified optimization problem is the following. It's the same optimization problem that I showed you before, only the only difference here is that the search scope or control now depends only on the current observation of the process x sub t. So that simplifies life dramatically. So now we're ready to characterize the optimal policy here. So the optimal search scope sigma star is fixed over time. And when it's interior, it's given by this formula. So it's a fixed point formula. And naturally, it relates to the cost and it's the marginal cost and in a very simple fashion. Now, you also see why log convexity is useful here. So you don't need to assume log convexity, but if we assume that the cost function is indeed log convex, then we have a unique solution whenever we have an interior solution here. Furthermore, this suggests immediate comparative statics as costs become more log convex, search scope declines, which is intuitive. Basically, that's the analog of increasing cost, reducing effort. Now, this idea that search scope is constant, that how ambitiously you search doesn't depend on the observations you've seen so far, is in line with various observations in the field. So, for instance, we see fairly constant R&D expenditures over time in a wide array of companies. Or when we look at mineral prospecting, that's actually an interesting application starting from the 50s. There have been these directives across various countries that suggest precisely the depth of each well that is to be inspected, regardless of other wells in the same area or the previous successes that have been seen in the same venture. All right, let me give you a quick intuition for where this is coming from. So recall the agents problem. So here, this is another copy paste of the same problem. And what we saw from proposition 1 is that the first term here, the maximum, is really not affected by local changes in the search scope. So what the agent effectively does is minimize the expected cost locally of her search. So let's think about it a little bit more, still in a hand-waving fashion. So again, proposition 1 tells us that minute changes in the search scope don't change the maximum. So that's not what we're worried about. Now, changing sigma is equivalent to, quote unquote, speeding up of time by a factor of sigma squared. That's just a feature of the Brownian path. So on a given path, we're essentially finding the efficient speed to hit our stopping boundary. So this means that we're effectively minimizing the cost per distance and time. So this is precisely the cost is C of sigma. The speed is related to sigma squared. So what we're doing is minimizing C of sigma over sigma squared. And the first order condition that corresponds to the minimization of this term is precisely our description of the constant search scope that's optimal. How about the stopping boundary? The next proposition illustrates its characterization. So the optimal stopping boundary at any point t with a previously observed maximum m is just a fixed distance from the observed maximum. So here we have a term that depends on the optimal search scopes that we already characterized and the cost of search. So higher costs are intuitively, here it's through sigma star, so I'm cheating a little bit, but higher costs are going to lead to a smaller distance here. And what you observe here is that the search, the stopping boundary has a very simple form. In fact, it's precisely the form that was in the original picture that I showed you for the stopping boundary. It's just a 45-degree angle line shifted away from m of t, shifted downwards by this constant amount. So let me give you a quick intuition for that. Think about a shifted process, tilde. So let's assume that we take our process and its related maximum and that just shifted them up by a constant A. Now we have here a linear utility. So the behavior in the tilde process should echo the behavior in the original process. So this means that the distance between the observed maximum in the tilde process and the stopping boundary is the same as in our original process, which in turn imply that m minus the stopping boundary, the level at m, is a constant, which is exactly what we see here. Now, this highly depends. Now, even though I don't have time to talk about risk aversion, you'll notice that at least from these hand-waving intuitions, the constant search scope doesn't depend on linearity of the utility function, while the precise structural or analytical form of the stopping boundary very much does depend on the linearity of the utility. So that's where risk aversion kind of becomes a little bit interesting. In terms of the outcomes, the expected project value is precisely this fixed distance from the maximum that identifies the stopping boundary. And I'll soon show you an intuition for that. And the expected duration looks somewhat similar and also has a very similar simple description. And that allows us to identify the expected payoff from search, which we'll soon use when we get to contracts between retrospective searchers and principals. Now, one interesting thing is that the expected payoff is precisely half of the expected maximum. That actually has a pretty nice intuition if anyone wants to ask me about it during the Q&A. But I will give you some intuition for this value of the expected maximum. So from proposition 2b, we have that the stopping boundary is this m minus a constant. So we'll call this constant the drawdown size. And the down size will be denoted by this d. So now notice two things. First of all, because the Brownian, from the continuity of the Brownian motion, for any realized stopping boundary, when you stop, you're precisely a distance d from the maximum. You're precisely hit g of mt. So this means that at the stopping time, the expectation of the distance here is precisely d. Now, in addition to that, x tau is a martingale with expectation 0. So for any stopping time tau, the conditional expectation of x tau is also 0. So now we can just use linearity of expectation and deduce exactly what the proposition stated, which is that the expected maximum is precisely b. The other elements of the proposition require a little bit more work, so I won't show them right now because I'd like to get to the application of contracting. So just to summarize the results that I showed you, we saw a constant search scope over time that depends on the log convexity of cost and a simple stopping boundary, which takes this form. So in the few minutes that remain, I'd like to tell you something about contracting with a retrospective searcher. And we're going to focus on commission contracts that are very common in the literature. They've been highlighted by Aguillon and Tirole in 1994, but they're prevalent in various applications. So you can think about real estate, where an owner searches for a buyer and then hires a real estate agent, pays them a retainer fee and a commission on the sales price, or an artist that looks to sell their art and pays or receives gallery showing fees and also a share of the purchase price, or research institutions that have been studied by a very nice paper by Jensen and Thursby, where a researcher seeks a breakthrough and they're paid a wage and get a fraction of the resulting patent rights, and so on and so forth. So in our model of principal contracts with an agent performing retrospective search, the principal is the residual claimant of the search outcome, but cannot conduct the search herself. And importantly, the class of contracts that we're focusing on are these commission contracts, where the principal offers the agent a wage or a fee of W, which is fixed over time, and a commission or a fraction alpha of the search outcome. The principal observes whether the agent is searching, but it's a standard moral hazard problem. So the principal doesn't observe the value of the project at any time t or the search scope of the agent. And let's assume that the agent has an outside option of 0 and she can quit at any time she wants. All right, so here's the main problem that we're facing. So the principal is trying to maximize the resulting reward that she'll get, which is just a share of 1 minus alpha of the maximum generated, minus the overall wage that she pays the agent. The agent in turn acts like a retrospective searcher. They're looking to find the optimal search scope and the time to stop search, so as to maximize their share of the pie minus the resulting cost. Importantly, now their costs are adjusted by the flow wage that they receive. All right, so let's focus on the agent's problem. So for the agent, we can follow a very similar characterization to our original characterization of proposition 2 and find their optimal search scope and their stopping boundary. The search scope is still going to be constant for the same reason. The only difference from the search scope in the original problem is that now costs are shifted downwards by the wage W. Now, importantly, the optimal search scope does not depend on the commission alpha. So if you get a small share of the pie, what will happen is that the search scope will not change, but the time that you spend searching will change. So in particular, our search boundary here, as alpha becomes very small, this is going to get closer and closer to the maximum you've seen. In other words, you'll be more and more demanding. So you'll search for a shorter period of time. Now, this can feed into the optimal solution for the principal. And if I had more time, I would show you precisely how to generate this. But you can quite directly derive the optimal wage and the optimal commission that are derived, and the consequent search scope for the agent. That now relates, so really what I'd like you to take out of this proposition are not the details, but rather first that we can solve this model quite easily. And the second one is that when you look at the optimal search scope, suddenly here we have the second derivative of the cost, which comes from the cost of incentives. Now, you could certainly consider particular families of costs to generate more observations. So let me show you one simple example of contracting with linear costs. So this is a situation where the costs are linear. And in that case, you can identify the individual searcher's search scope and expected payoff. So in this case, as the fixed cost declines, the search scope increases. So this is the search scope increasing with A. As the marginal cost increases, the search scope declines, which is kind of in line with our intuition. And the resulting profit can be derived from our proposition 3, and that's just A over B squared. Now, if we place this in our optimal contract, the search scope declines from 2A over B to 4/3 of A over B, and the agent and principal share the spoils equally. More interestingly, the overall surplus that they generate is 8 over 9 times A over B squared. So in for this particular class of costs, regardless of the precise parameters, there is a loss of about 1/9 or 11% of the surplus due to these agency costs. Let me conclude. So what I tried to show you is a model of retrospective search. So this is a model of search with correlated observations and experimentation. The optimal policy entails a constant search scope and a simple drawdown stopping boundary. And we think this analysis can be useful for various settings. So I showed you one example of commissioned search. John and I are also looking at various constrained searches, constrained by either institutions or by cognitive limitations. We're also looking at team search together with Dorek Chedeman. Thank you very much for listening, and I look forward to talking with you all.
So thank you, Leeat, and good morning. I think it's quite early for you, but thank you for joining us now. And we can take a couple of questions from the audience. Let me just, so if anybody has questions, they can ask now. Am I?
I see Hans has a question.
Yeah, just a question, thinking of the speaker 2 episodes before that. Would a concept like idea of loss aversion, could that play a role in this? Because I can imagine that once you reach a certain level, MT, that after that, whatever you reach becomes more disappointing. So would that be something that could be accommodated in this model, or is this already implicit?
So I think it wouldn't. I don't quite see how it would change things unless you have maybe of how the reference point changes. So at every point in time when you stop, you get the maximum. So if the maximum serves as your reference point, every time when you assess the future, you're in the gains domain, because you can't do worse than the maximum you have in hand. And
Yes.
whenever you stop, you get the maximum.
You don't have a utility function included, but you could imagine that once you reach the first time your maximum, that after that, I don't know how you would express that, perhaps searching costs become higher or something higher.
So if costs vary in time, dependent time, then that's a much more involved technical problem, right? Because then you lose the stationarity. That's even this problem is very difficult. So that I think there isn't a ton of. I wouldn't have a ton of hope unless you put very particular functional forms, perhaps.
Yeah. Okay, just an idea. Thank you.
Yeah.
Yes, I was wondering how to use this kind of techniques in a collective choice or welfare setting. So I don't know if you have ideas about that, but maybe one possibility is to think of the whole society searching. And if there are many people in the society, each one is making or not some slight progress, and then the aggregation of these many small events, it looks as something like a normal distribution because there are many of them. And then maybe we can think of the collective process of finding a new things in this spirit. I don't know, it's just a random thought like that.
Yeah, it's we thought in this direction. So we have one paper that is almost done that is in this direction, but not quite, and then another thought that's related to that. So the stuff that I mentioned at the very end with Doruk, we actually look at innovation by teams. So we're thinking of small groups, and this is exactly what you described, the situation where if you and I are searching together, then there are externalities from our search. I invest in search scope, you do, and we get the sum. The question is then when to exit for each one, right? So we both learn some technique, and I decide that I've had enough, and you might continue improving your techniques and get your own, the resulting maximum. So that allows us to kind of characterize exit waves and also the various investment properties in these games. The other option that we thought about for embedding this in a collective choice problem is maybe has kind of the decision rule that you had in mind, where we search as a team, and now we're going to vote on when we're going to stop searching. You can even vote on the search scope. You know, we each say our desired scope and choose the median if you wanted to impose this on society, or we choose it individually. So you can solve that model as well. Yeah.
Any more question?
Let me ask a question, quick question. So it's related to the previous question. Is the optimal contracting problem also with multiple agents? You know, if all the agents are searching, so how should the principal design these contracts? So if there are multiple agents searching, would that also be quite easy to solve after your initial results, the fundamental result?
Okay, I'm afraid to say anything is easy. I'm sure you can come up with a setting that wouldn't be easy. But yes, we started out with one agent because contracting with teams, you know, this is something the literature has already identified the various forces that introduced. So it seemed easier to kind of isolate the impacts of retrospective search in this context with one agent. But yes, this is very amenable. This setting is very tractable, as it turns out. So yeah, you could do whatever you do, you know, in your favorite contracting model here too.
Thanks.
Okay, so we still have time for a couple of questions.
May I ask question? Yes, I understood the stopping rule is endogenous, is the shift down of these 45 degrees. But now suppose that you are searching, but you have a terminal date. In your setting, you could keep charging, and you have to decide when to stop. But now suppose that you are going to stop. So I'm looking for something in a website, but I need the object. So how this introduces, because now you are some of the properties of the stationarity.
That's right. So the constraint search stuff, we looked exactly at that. It's a very natural question. So if you want to also endogenize the search scope, that's actually a difficult problem. Again, for similar reasons to what I said to Hans in the beginning, it breaks stationarity, right? Because now part of the state space is how much time you have left if you have a pre-prescribed scope. But what we can do is fix the search scope and find the optimal time window for which you should search, or identify the resulting payoffs from any time that you search. And actually, there's a very nice formulation of this. So it turns out that there is a ratio, now I don't remember exactly, but it's 1/√2 pi, I think, of the optimum, or from this limited search scope. It's a very natural question, because if you go back to the classic, Stigler in 1961, when he started thinking about search, that's exactly how he thought about search. He thought, kind of an analogy to classical hypothesis testing in the sampling world, he thought of getting a sample of observations fixed in size and optimizing over the size of that set. So essentially, the problem in our context is just we're reinventing the wheel. It's Stigler in 1961, but with correlation between samples.
Thank you very much.
So if there are any more questions, otherwise we thank Leeat, especially for waking up so early. It was a great talk. So we are ending the Paris transmission. So we have now vote of thanks. So Arunava wants to say something, probably. And anybody else on behalf of the society.
Okay. No, I just like to thank the organizers. I mean, this may appear to be a simple task compared to the task of organizing a face-to-face conference, but it certainly wasn't. And must thank Kanishka and Diego and Andre and who am I missing? David. All of them for their effort, and thank everybody, the speakers, and hope to see you guys in person in 2022. Okay, so thank you very much. Thank you.
Thanks for organizing that. Bye.
Hans, you want to add some?
Okay,
so we are concluding in Paris, and in 2 hours we'll be moving to New York. There will be another transmission. So if anybody has more questions you want to ask, so you can join us. I know it's difficult for people living in Asia. However, Europeans they can come, and so those who won't be able to be there, like. The current situation compelled us to organize this online conference. It was a great conference, definitely. And in 2022, we are planning to have the face-to-face meeting, the 16th meeting in Mexico City. So we hope you can join us. Thank you so much.
Thank you.
Bye. Thank you very much.
Thank you.
Bye-bye. Thank you.
Bye.
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 Bye. Bye-bye, Ramzi. So Hans, you'll be joining the next.
Yeah. So remind me, it is at 5 European time.
That's right. That's right.